Mahanwar madam.
Yes, sir.
करूयात सुरू मॅम.
Okay, sir. Good morning, all. It gives me immense pleasure to extend to you a very warm welcome on Ray Shikshan Sanstha's Abasaheb Marathe Arts, New Commerce and Science College, Department of Chemistry in association with Royal Society of Chemistry, West India, who has clubbed all of us for lecture series UG and PG students. Just little housekeeping before we get started. If you have any questions during the presentation, please type them into the chat box. To keep the quality of sound during the meeting, please mute yourself when you are not sharing. I request Dr. H.N. Akolkar sir to preface today's webinar.
Thank you, ma'am. Thank you. First of all, good morning and welcome all. I welcome you all on behalf of Ray Shikshan Sanstha, Abasaheb Marathe Arts, New Commerce and Science College, Rajapur. Our college, Abasaheb Marathe, it is situated in Rajapur district, Ratnagiri, which is affiliated to University of Mumbai. And our college is well known and renowned and prestigious one and located in rural area. We are focusing on giving quality education to the needy, deprived and downtrodden students of rural and Konkan region. So here we have planned to organize a lecture series in association with Royal Society of Chemistry. So Royal Society of Chemistry is a learned society of United Kingdom with a goal of advancing in chemical sciences. The headquarters of society is in London, along with the branches office in United States at the University City Science Center in Beijing and in Shanghai, China, and in Bangalore, in India. So Royal Society of Chemistry, West India, organizes a wide range of events to support the chemical scientists at all stages in their career, including frequent lectures, symposia, popular science events, and activities for postgraduate and graduate students. Dr. Suvarna Kulkarni has helped us to organize this event. And here we have organize a lecture series that will be a milestone to the rural student by listening the renowned resource persons, so that student will get motivated and will try to achieve their goals. This lecture series is not only beneficial to our college, but also it is also useful to nearby colleges in Konkan region and in Maharashtra. So for this, I am very much thankful to the Society of Chemistry for approving us this lecture series, and also thankful to the our today's resource person, Dr. Suvarna Kulkarni sir, for giving us opportunity to organize this lecture series. Thank you very much, sir. And also, I am very much thankful to the Rayat Shikshan Sanstha, who gave us opportunity to show the interest to collaborate with Royal Society of Chemistry and to organize this event. So I am very much thankful to Rayat Shikshan Sanstha and Royal Society of Chemistry. Thank you very much.
Thank you, sir. Now I request Principal of our college, Dr. G.D. Harale sir, to give presidential address to our students.
Harale sir, now you can yes. Harale sir, your voice is not, sir, तुमचा आवाज येत नाहीये, अनम्यूट.
हा, येतोय आवाज?
येस सर, येस सर,
आवाज येतोय?
येस सर, बोला सर. येस सर.
ओके. आबासाहेब मराठे महाविद्यालय राजापूर आणि जगविख्यात रसायनशास्त्र विभागातील एक संस्था रॉयल सोसायटी ऑफ केमिस्ट्री वेस्ट इंडिया, या दोन्ही ब्रँच मधून आपण एक संयुक्तरित्या केमिस्ट्री विषयाची लेक्चर सिरीज आयोजित करत आहोत. या लेक्चर सिरीजच्या आयोजनासाठी आमच्या महाविद्यालयातील रसायनशास्त्र विभाग प्रमुख डॉक्टर अकोलकर सर, डॉक्टर ससाने सर, महानोर मॅडम यांनी विशेष परिश्रम घेतलेले आहेत. त्याचबरोबर आमच्या संस्थेतील काही पदाधिकाऱ्यांनी त्याला मान्यता दिलेली आहे. त्याचबरोबर ही लेक्चर सिरीज आयोजित करण्यासाठी विशेषतः मी सुवर्ण कुलकर्णी सरांचं विशेष आभार मानतो की त्यांनी ही लेक्चर सिरीज करण्यासाठी त्यांनी विशेष प्रयत्न केलेले आहेत. आणि या ठिकाणी काही गोष्टी सांगायच्या आहेत की आमची संस्था रयत महाराष्ट्रातील 15 जिल्हे आणि कर्नाटकातील 1 जिल्हा अशा 16 जिल्ह्यामध्ये विभागली गेलेली आहे. आणि आमच्या संस्थेचे संस्थापक जे आहेत डॉक्टर पद्मभूषण डॉक्टर कर्मवीर भाऊराव पाटील यांनी ही संस्था 1919 मध्ये स्थापन केली. त्या स्थापनेमागे त्यांचा उद्देश होता की ग्रामीण भाग, जे गरीब मुलं आहेत, दुर्गम भाग आहे, अशा त्यावेळेला अशा मुलांना शिक्षण मिळावं, हा त्यांचा हेतू या मागचा होता. त्यासाठी त्यांनी अगदी तन मन धन लावून त्यांनी या शिक्षण संस्थेची उभारणी केली. आज छोटंसं रोपटं लावलं होतं, त्याचं वटवृक्ष तयार झालेला आहे. ही संस्था आज भारतात नव्हे तर आशिया खंडात सुद्धा एक नामांकित संस्था आहे. ज्या संस्थेमध्ये साधारणपणे 13,000 सेवक कार्यरत आहेत. 4.5 लाख विद्यार्थी या शिक्षण संस्थेमध्ये शिक्षण घेत आहेत. जवळपास 42 सिनियर कॉलेज आहेत, 450 हायस्कूल आहेत. एकूण शाखांचा जर विचार केला तर 770 शाखा या वेगवेगळ्या प्राथमिक, माध्यमिक, ज्युनियर कॉलेज, सिनियर कॉलेज अशा शाखा आहेत. इतकी मोठी संस्था नावाजलेली संस्था आहे. आणि या संस्थेबद्दल बोलायचं म्हणलं तर जे संस्थापक होते त्यांनी इतका त्याग केला. गरीब विद्यार्थ्यांना शिक्षण कसं मिळेल, दुर्गम भागातील विद्यार्थ्यांना शिक्षण कसं मिळेल यासाठी प्रसंगी आपल्या पत्नीचं मंगळसूत्र सुद्धा त्यांनी गहाण ठेवून मुलांना हॉस्टेलला जेवण सुद्धा दिलेलं आहे. इतकं त्याग त्या थोर व्यक्तीचा, महान व्यक्तीचा आहे. त्यामुळंच आज पश्चिम महाराष्ट्रात विशेषतः आणि काही कर्नाटकातील एक जिल्हा आहे बेळगाव जिल्हा, या जिल्ह्यामध्ये त्यांनी शिक्षण पसरवलं, जे ग्रामीण भागातील मुलांना शिक्षण मिळालं. या ठिकाणी आपल्या रयत शिक्षण संस्थेचं हे जे राजापूर ठिकाण आहे हे सुद्धा एक दुर्गम भाग आहे की या कॉलेजच्या आजूबाजूला एक सुद्धा घर नाही. साधारण 2 किलोमीटर अंतरावर तुम्हाला काही घर दिसतील. त्याच्या आजूबाजूला आहे, इतका दुर्गम भाग आहे, डोंगराळ भाग आहे. इतक्या दुर्गम भागात सुद्धा रयत शिक्षण संस्था कार्य करत आहे. आणि त्यामध्ये आपलं जे हे कॉलेजचं युनिट आहे त्यामधले हे शिक्षक आपले प्राध्यापक जे आहेत ते असे नवीन नवीन उपक्रम राबवण्यासाठी विशेष प्रयत्न करत आहेत. त्यासाठी आपल्या महाविद्यालयात जे आज लेक्चर सिरीज आयोजित करतोय आपण ती खूपच छान आहे. मला अभिमान आहे की त्या लेक्चर सिरीजचा फायदा केमिस्ट्री विषयातील बहुतेक प्राध्यापकांना होईल, बहुतेक मुलांना होईल. आणि हे लेक्चर सिरीज जे आपल्याला मंजूर करून देण्याचं काम जे डॉक्टर सुवर्ण कुलकर्णी सरांनी केलं त्याबद्दल मी त्यांचं विशेष आभार मानतो आणि धन्यवाद देतो. या लेक्चर सिरीजला माझ्या शुभेच्छा आहेत. आमच्या संस्थेच्या वतीनं, महाविद्यालयाच्या वतीनं या लेक्चर सिरीजला शुभेच्छा आणि मी थांबतो या ठिकाणी.
Thank you, sir. Now we will turn the time over to speakers. Now I request Dr. S.S. Sasani sir to introduce our first speaker for day, Dr. Suvarna Kulkarni sir, to our esteemed audience.
ससानी सर ऐकून येते, म्यूट आहे.
Okay. Good morning to all of you. Thank you very much, Mahanavar madam. So we are grateful to him for accepting our invitation and becoming a chief guest of today's lecture series. Our chief guest does not require an introduction as he is a well-recognized person in the field of chemistry. But it is the format of this lecture series. So let me catch this opportunity to introduce today's chief guest, Professor Dr. Suvarna Kulkarni sir. Professor Dr. Suvarna Kulkarni sir received his PhD in the field of organic chemistry from University of Pune in 2001. After his PhD, he pursued his postdoctoral research at Academia Sinica Taipei and University of California, Davis. He returned to India in late 2008 and held a faculty position at IACS Kolkata prior to joining the Indian Institute of Technology in 2009. He subsequently rose to the rank of full professor in 2016. He is recently appointed as an institute chair professor and also as an associate dean in academic programs of IIT Bombay. His current research interests include diverging never ways to efficient chemical synthesis of complex glycoconjugates implicated in various infectious diseases. His research protocols, JAX, Angmanta Chem, Chemical Sciences, and Organic Letters. These are very reputed journals in the field of chemistry and having the high impact factors. Then he also published his work such as in Nature Protocols, also has been highlighted in chemistry world, research matters, Hindu, Saka, and Lokmat. Suvarna Kulkarni was a short-term visiting professor at Taiwan in 2014. He is a fellow of the Royal Society of Chemistry. He is a recipient of the CRSI Bronze Medal for the year 2017 and Dr. S.C. Srivastava Young Scientist Award in 2016. He is a member of the editorial board of Carbohydrate Research and Chemistry Select, which is a very high impact factor journal, internationally reputed journal. He is also a guest editor of Frontier and European Journal of Organic Chemistry. He has recently received a research dissemination award at IIT Bombay. Most importantly, he was selected by the student for the Excellence in the Teaching Award at IIT Bombay in the year of 2017. And very recently, for the prestigious Professor S.P. Sukhatme Award for the Excellence in Teaching in 2020. So, with this brief introduction, I request to Honorable Professor Dr. Suvarna Kulkarni sir to deliver his talk on organic stereochemistry to our student. Please, sir.
धन्यवाद. सर्वप्रथम मी आपले हरळे सर आहेत त्यांचे आभार मानू इच्छितो की मला त्यांनी महत्त्वाच्या कार्यक्रमामध्ये सहभागी केलं आणि रॉयल सोसायटी ऑफ केमिस्ट्री तर्फे मी आपल्या कॉलेजचे आभार मानतो की तुम्ही हा कार्यक्रम करताय. ऍक्च्युअली कार्यक्रम तुम्ही करताय, रॉयल सोसायटीचा फक्त सपोर्ट आहे. तर त्यामुळे सर्वप्रथम कॉलेजचे आभार आणि या सगळ्या मागचे सूत्रधार आपले हेमंत अकोलकर सर यांचे मनपूर्वक आभार. गोष्ट आणि कीर्ती मॅडम. तर ऍक्च्युअली मला कॉलेजमध्ये स्वतः यायला आवडलं असतं प्रत्यक्ष, पण आपल्या करोनामुळे येता आलं नाही. आणि हरळे सरांनी मराठीत बोलायला सुरुवात केल्यामुळे मला अतिशय आनंद झाला. मला आता मी मराठीमध्ये बोलतोय कारण मला आपल्या जे सगळे मित्र जमलेले तिथे त्या वेळेत सगळे ज्या झूम प्लॅटफॉर्मवर त्यांना सांगायचं की माझं सगळं शिक्षण मराठीत झालं. पहिलं जे प्राथमिक शिक्षण असतं 1ली ते 10वी नूतन मराठी विद्यालयामध्ये झालं आणि त्यामुळे मराठी भाषा ही आपल्याला कुठल्याही प्रकारचं आपल्याला येत नाही. त्यामुळे आपण पुढे कारण शिकू शकतो, इंग्रजी असो किंवा मराठी असो, त्याने काही फरक पडत नाही. आपल्याला त्यातली जी संकल्पना आहे मूळ कुठल्याही अभ्यासाची ती कळली पाहिजे. तर रयत शिक्षण संस्थेचं कार्य हे दैदिप्यमान आहे, त्याचा काहीच म्हणजे सगळ्यात जे जग जाहीर आहे. त्यामुळे आपल्या संस्थेने मला इथे बोलवलं यात माझा खूप मोठा सन्मान मी मानतो. आणि आपल्याला थोडा वेळ असल्यामुळे मी जास्त बोलत नाही, मी आपल्या याला सुरुवात करतो स्टिरिओ केमिस्ट्री. तर आज आपण बोलणार आहोत ते स्टिरिओ केमिस्ट्री विषयी. आणि पहिल्यांदा म्हणजे मी स्लाइड शेअर करतो आणि विषय आपला असा असल्यामुळे मी इंग्लिशमध्ये बोलेन, पण तुम्हाला काही शंका असेल तर तुम्ही मला विचारू शकता कुठल्याही.
स्टुडंट्सला जर काही शंका असतील तर तुम्ही चॅट बॉक्स मध्ये तुमच्या शंका लिहू शकता.
ओके. आता ऍक्च्युअली स्लाइड शेअर करायच्या आधी व्हॉट आय विल डू, तुम्हाला जर माझा व्हिडिओ तुम्हाला पूर्ण स्क्रीन भरून दिसत नसेल तर तिथे पिन व्हिडिओ म्हणून एक फंक्शन असतं. आय थिंक तुम्हाला दिसतोय, तुमच्या संयोजकांनी तसं केलंय. तर पहिल्यांदा मी चालू करण्याआधी स्टिरिओ केमिस्ट्री म्हणजे 2-3 गोष्टी मी तुम्हाला मॉडेलने दाखवतो आणि मग मी स्क्रीन दाखवतो. हा मॉलिक्यूल सगळ्यांना माहिती आहे, हे 2 कार्बन ॲटम आहेत. हा इथेन आहे C2H6 राईट. आणि यू कॅन सी हे त्याला आपण म्हणतो स्टिरिओ केमिस्ट्रीमध्ये फ्लाइंग वेज स्ट्रक्चर F ऑफ इथेन राईट. आणि हेच आपण जर असेही बघू शकतो आणि हेच आपण टिल्ट केलं तर हा न्यूमन प्रोजेक्शन फॉर्म्युला तयार होतो इथेनचा. अशा याच्यात आपण असं वळवलं तर हा इथेनचा न्यूमन फॉर्म्युला तयार झाला. आणि मला जर याचा फिशर करायचं असेल तर असं वळवायला लागतं आणि हा फिशर प्रोजेक्शन फॉर्म्युला तयार झाला. तर स्टिरिओ केमिस्ट्रीचा अभ्यास मुख्यतः सिमेट्रीचा अभ्यास आहे. लेट मी गिव्ह यू एन एक्झाम्पल. This is a molecule of ethylene, dichloroethylene. इथे डबल बॉन्ड आहे. तर याला प्लेन ऑफ सिमेट्री आहे का? तर नाही आहे. प्लेन ऑफ सिमेट्री इथे बघायला लागेल तर नाही आहे. पण याला C2 ऍक्सिस ऑफ सिमेट्री आहे. हा मॉलिक्यूल जर मी 180 डिग्रीज मध्ये असावा तर मला सेम मॉलिक्यूल मिळणार आहे. सेम मॉलिक्यूल मिळणार आहे. त्याला सिमेट्री असा. प्लस याला सेंटर ऑफ इन्व्हर्जन आहे. म्हणजे इथून जर मी गेलो इथे मधल्या पॉइंटला इथे गेलो, इथून निघालो मधल्या पॉइंटला आलो इथे आलो, याला सेंटर ऑफ सिमेट्री आहे. हेच जर मी तुमचा सिस डायक्लोरोइथेन घेतला तर आता तुम्ही सांगू शकाल याला प्लेन ऑफ सिमेट्री आहे का? आहे. इथे मिरर प्लेन आहे, पण याला सेंटर ऑफ सिमेट्री आणि याला C2 ऍक्सिस आहे का? आहे, पण तो असा नाहीये, तो असा उभा आहे. म्हणजे आपल्याला मॉलिक्यूल हा असा वळवला मी 180 डिग्रीज फ्रॉम तर मला तो C2 ऍक्सिस ऑफ सिमेट्री येतो. तर स्टिरियोकेमिस्ट्रीचा अभ्यास करताना पहिल्यांदा आपल्याला सिमेट्री अभ्यास करायला लागतो. ओके, नाउ लेट मी शेअर माय स्लाइड्स. Okay, right. So what we are going to do first is we are going to start looking at the elements of. So okay. So this is the organization of my talk. First, I'll be talking about how do we recognize the element of symmetry and use that information to decide whether the compound is chiral or achiral. Then we are going to differentiate between various types of stereoisomers, enantiomers, diastereomers. Then we'll be talking about absolute and relative configuration. Then we will look at 3D and 2D representation like Fisher and so on, and Newman. And if time permits, I will talk about atropisomers. So before I start, let me ask Professor Akulkar, sir, मला किती वेळ आहे माझ्याकडे?
सर काय प्रॉब्लेम नाही, तुम्ही पूर्ण घेतलं तरी चालेल.
फाइन सर, थँक यू.
येस सर, येस.
जास्तीत जास्त 1 तास, पण 40
Okay, sir, no
1
problem.
तास. Okay.
Yes sir, yes.
And what I would expect is everyone, please, okay, yeah, you can type your questions in the chat box if you have any. I'll also ask in between. So let's begin. See, when we talk about isomers, what are isomers? Isomers is basically different molecules with same molecular formula. Right. So the connectivity is different. These two are isomers. So we have a cis dichloroethane, ethylene, and trans dichloroethylene. These two are stereoisomers. So two types you can say. One, they are constitutional isomers, where we are changing the connectivity of the bonds and we are also changing the position of atoms. Such isomers are called as constitutional isomers. Whereas if you're not changing the connectivity, they are called as stereoisomers. If you are changing the position of atoms, they are constitutional. Changing only the orientation, they are stereoisomers. Now, this is the main question as to what does chirality mean? And many of us think that presence of chiral center is chirality. Right. So let me tell you that chiral center, a chiral compound may or may not have a chiral center, and vice versa. That means it is not necessary that if you have a chiral center, the compound will be chiral. So then what is the meaning of chirality? So chirality is a basically Greek word. It is derived from this word called as chair. And the meaning of chair is handedness in Greek. Handedness. So we say right-handed or left-handed. That is the meaning of the word chair. And from there, chirality has come. So simple definition of chirality, in my opinion, is you just look at the object and look at the mirror image. If the object and the mirror image, they are non-superimposable, they are chiral. If the object and mirror images are superimposable, they are achiral. So as I told you, you have a left hand and right hand. These mirror image, right? But they are non-superimposable. And therefore, our hand is a chiral object. Now, there is no question of chiral or stereo center. Here, there is no stereo center, but the hand is chiral. Right. Now, here, which of these are chiral? Can you tell me which of these are chiral? You can type your answer. We can go one by one. Shoe, is it chiral? Will the left hand shoe will fit your right hand? Okay, yes, you're right. Thorat. So this is chiral. What about sock? Is it chiral? You can use any sock on any foot, right? So sock, if you look at sock and glove, they are not chiral because you can use any pair. But if you have a finger like this in a sock, this is chiral. This one is chiral, this one is chiral. So except these two, all others are chiral. Because simple, because their mirror image is non-superimposable. Right. So now let me come to the point of molecular geometry and symmetry and how does it related to stereochemistry. So basically what I'm going to do now is going to tell you how to find out symmetry elements in the molecule. And if there are symmetry elements other than C2 or other than Cn, the molecule is achiral, and I'll come to this point. So basically why we want to study molecular geometry and symmetry, because based on that, we can have important inferences. We can classify them as chiral or achiral based on the symmetry. Right. So here we have this molecular model. What we do, we start with the original position, we carry out symmetry operation, and we get a new position. If this is superimposable, if we come back to the original position, we say that the molecule possesses element of symmetry. And I will give you an example. So let's say you are looking at the star, and I have marked black point here. So if you rotate it by 72 degrees like this, through the axis passing through the center, you will get exactly similar looking object, right? And this you can do 72 degrees, you can do 5 times to come back to the original point. So if you rotate a molecule around an appropriate imaginary axis by an angle 360 by n, here n is your number of times you have to turn it to get the original one. So this is your Cn. Then we call that this has a C5 axis because you can do it 5 times and the angle is 72 degrees. Similarly, I showed it to you. If you're talking about trans dichloroethylene, from the center you can rotate by 180 degrees. So 360 by 180, that is equal to 2. So it's a C2 axis of symmetry. And cis one, see, our nature is full of symmetric objects. We have C2 symmetry, right? Like butterfly, we can have our 2 sides can perfectly reflect through a mirror, right? And so if you have a cis dichloroethylene or cis dichloroethylene, I'm sorry. So you can see here you have a mirror plane, and also it has a C2 axis of symmetry which passes through this. Now this doesn't have a mirror plane, but this has a mirror plane. So mirror plane we call as sigma, C2 axis of symmetry we call as Cn, C2, C3, C4, C5, and this is I, or inversion center. Now this molecule of trans dichloroethylene has an inversion center. What is the inversion center means? If you start from one atom and you go through the center, you reach the same atom on the other side. Similarly, you start from this hydrogen, you cross the center, exactly same distance on the other side, you find other hydrogen. So nature has many objects which have inversion center, right? So this is the inversion center, and this is more difficult to grasp, this symmetry element. This is called as imperfect axis of symmetry or alternating axis of symmetry, right? So what we are doing, this is a hybrid operation. So you have to do first a Cn, and then in the plane perpendicular to the Cn axis, you have to do a reflection in the mirror. So to give you an example, you look at this methane. This is the horizontal axis, and through which you do a C4 operation. C4 means 90 degrees, 360 by 4, that is 90. So what will happen? This A point will come here, and B point will go behind, and D will come here, and C will come here. You are just rotating by 90 degrees. Like this molecule, you are moving like this, horizontally. And then you reflected in the mirror plane, you get the same molecule back. Then we call that this has alternating axis of symmetry, or in other words, methane has, it is denoted by S, so we call methane has S4 axis of symmetry. Now, how does it all matter? For chirality, okay, I also want to show you something later on, or maybe now. Whenever you have time now, please write down this site, http://simotter.org. So if you click this simotter.org, anyway, so we'll see it later if time permits. This is a website which is free, and this will help you to play with the molecules. It will allow you to rotate the molecules and find out all the symmetry axis and all the complicated molecules there which are present. So they have done amazing job. You can look at it later. Now, coming back to the concept of chirality, if your molecule has a plane or inversion center or alternating axis, it cannot be chiral. It has to be achiral. One of these will make the molecule achiral. If the molecule doesn't have any of these, it's chiral. However, it may have a C2 or CN axis, both. So a molecule having only CN axis is chiral. But all the other elements, it makes it achiral. And this is what I said, that please remember that presence of a chiral center. What is chiral center? You have carbon with 4 different substituents. Is neither necessary nor sufficient requirement for molecular chirality. That means even if you have a chiral center, the molecule as a whole can be achiral. And even if you don't have any chiral center, the molecule as a whole can be chiral. And I will give you examples as we go along. Now let's take a look at it. Right, this is a bicyclic ketone, and I'm saying that D is chiral because D does not have any element of symmetry. If you look at A, it has a mirror plane which passes through this oxygen and midpoint of these two sides. This also has a plane of symmetry. Oxygen, carbon, this carbon, and midpoint of this side. This also has a plane of symmetry. Oxygen, carbon, carbon, carbon. But this doesn't have axis of symmetry, plane of symmetry, alternating axis of symmetry. Therefore, out of these 4, only this compound is chiral. Okay, so are there any questions so far? Fine. So molecules, right, we can classify them into 2 stereoisomers, 2 types of stereoisomers. One is enantiomer, other is diastereomers. And you know that enantiomers are basically molecules which are related as molecule and its mirror image. If it is non-superimposable, we call it enantiomer. If it's superimposable, it's identical. And diastereomer cannot be related as a mirror image of the molecule. So this one, why study of chirality is so important? You know, we take many medicines. When we take each type of medicine, many medicines are chiral in nature. And it is important to do a quality control before the medicine is sold to us. Because see, these are, I'm showing you 2 cases here. This compound is called as thalidomide. And the RI enantiomer of this compound is used as a drug against nausea. So pregnant women, they have this vomiting sensation, they take this drug. But if there's a impurity of S isomer, this causes fetal damage. म्हणजे बाळाला त्रास होऊ शकतो पोटातल्या. त्यामुळे किती महत्त्वाचं आहे? It's very important that you have 99.99% purity or 100% purity, because you cannot afford to have any of these S isomer in the drug. Similarly, you see this is a Vicks Vaporub, active ingredient of Vicks Vaporub inhaler. All of us, we take this. But you change this chiral center to this, R to S, this becomes a drug. It's a CNS stimulant drug, which is called as speed. It's methamphetamine. It's a drug called speed. So it's a controlled substance, right? And if you have seen this serial web series Breaking Bad, this is a compound called as crystal meth in that series. So this slide tells you that it is very, very important for us to identify what is the enantiomer purity of your sample before you give it as a drug. Now, how do you measure enantiomer purity? That's the next question. So this is about enantiomers, right? About diastereomers and enantiomers, they have identical properties, identical physical properties in a chiral medium. The moment you place them in chiral medium, such as our body, they behave differently. That's why your R isomer is behaving differently, S isomer is behaving differently. Now, diastereomers, anyway, they are different compounds. They are chemically as well as physically different. They can be chiral or achiral. And to give you an example, this is on your screen, you see fumaric acid and maleic acid. Fumaric acid has a high melting point because you can see the packing is very nice, therefore it gives a nice solid, and the melting point is 299 to 300. Whereas if you these isomers, this will form anhydride upon heating, right? This cannot form because they are apart from each other, and the melting point is less. Now, these are also diastereomers, right? So if you have two chiral centers and you change only one of the chiral center, if you change both, they will become enantiomers. If you change only one, they will become diastereomers. So diastereomers have some matching, some not matching chiral centers. That makes the diastereomers. Okay, so are there any questions so far? I think all of you know what are diastereomers, what are enantiomers. Right. Okay, so if we want to know what is the optical purity of a compound, the only way to know is you use a machine called as polarimeter. Right. Polarimeter helps you to record the optical purity of the compound. How do you do it? So first of all, polarimeter is the machine equipment that helps you to measure the optical rotation. So your chiral compounds are capable of rotating the plane of plane polarized light, either to the right or to the left. Okay. So if they rotate to the right, we call them dextrorotatory or small d, and or plus enantiomer. If they rotate to the left, we call them levorotatory or small l or minus enantiomer. All right. So this diagram shows you nicely that if we just take a beam of light, it has an electric component that oscillates into all directions, and it will be difficult to measure the rotation in the plane. So to begin, we need to pass it through a polarizer or a filter to cut all the other lights and just keep one plane. So once you get a plane polarized light, you then pass it through the medium. If your compound is chiral here, it will rotate the plane of polarized light either to the right or to the left. And here you have a lens. So if light passes through directly to your eyes, you know that this compound is not chiral. If you see the darkness, you know that the compound is okay. Your compound is chiral, optically active. And then you can rotate this dial so that the light passes, and this correction is called as alpha, or rotation, or degree of rotation. And what we measure is actually alpha into square bracket lambda. This is called a specific rotation. And the specific rotation is calculated by using this formula, alpha square bracket lambda or alpha d, capital D, and that capital D we use because we are using a sodium D line. And that's why basically any wavelength is okay. So not necessarily D line, you can use any other thing. But typically we use D line, so we write alpha D. And then alpha divided by L into C, where L is length of vessel in decimeter, C is concentration. This is specific rotation. Now, this is a point to remember. When you have two enantiomers of the same compound, both will have same optical rotation, but opposite sign. This sign has nothing to do with R or S. Meaning, R can be plus or minus, S can be plus or minus. You cannot say that minus means R or plus means S. However, if you know that this is R, then certainly this is S. But directly there is no correlation between R and S and plus and minus. Plus and minus is decided by actual experiment, whereas R and S is done by our using our CIP rules, and I'll be talking about that in a bit. So please note that sign of rotation does not tell you anything about absolute configuration or relative configuration. All right, are there questions so far? And don't feel shy. This is your college has made all the efforts to bring speakers for you, so you should take advantage of that. If you have questions, don't feel shy, just ask. Okay, this is how we calculate optical purity. Now, optical purity is also sometimes called as enantiomeric excess. Now, let me test what you know by enantiomeric excess. If I say that I have 95% enantiomeric excess of a certain enantiomer, 95%, what is the meaning of it? What is the individual proportion of two enantiomers? We have a mixture having 95% enantiomeric excess. What does it mean? You can type your answer. What is the ratio of these two isomers? Don't look at this formula. They're not related with the formula. I'm just asking simple question. When I say we have 95% enantiomeric excess, what is the meaning of that? You have two enantiomers. What is their proportion? So if you have two enantiomers with one having 90%, right, and the other having 10%, that means you have an enantiomeric excess of 80%. If you have one enantiomer 97.5% and the other enantiomer 2.5%, that means you have an excess of 95%. Why? Because the 2.5% positive is cancelled by 2.5% negative, and therefore you are left with 95% only. So that means enantiomeric purity is very, very important. And this is how this is a formula, and formula is very simple. You just look at the observed value and then you divide it by value of a pure enantiomer. So let me give you an example. I'll give you 2 minutes to solve this. And the formula is simple. Observed, rotation of observed divided by rotation of pure, multiplied by 100. That's enantiomeric purity. So this is a real life situation that you face. So this is a specific rotation of S2 iodobutane. That means this is a rotation of pure enantiomer. That means this is your denominator. And the question is, determine the percent composition of a mixture of R and S if the observed rotation of a mixture is minus 3.18. If we plug it in these figures, we get 3.18 divided by 15.90. So can you give me the answer of this? What is the proportion of these two isomers, R and S? And which one is major? So, see, one of the troubles with this online medium is that you don't know whether you're talking alone to the computer or are there people in the audience. Because this is what some advantages are there for online medium, that I don't have to travel. I can sit at my office and give a talk. But the disadvantage is that there is no connection between the audience and you. Right? Anyway, because we have limitation of time, looks like nobody is able to solve this. So you can see this is how you solve it. You have optical purity 3.18 divided by 15.90 multiplied by 100. So it's with 20% purity. That means one is 60%, the other is 40%. 40-40 cancels and 20% remains. So it's a 60-40% mixture. So this is about optical purity. Okay. Now that brings me to the next point, that is absolute configuration. And the system, we all know R configuration and S configuration. Now, do you know R and S? At least say yes and no. At least type something so that I will know that I'm not alone here. Yes, that's great. So this is a system of naming the chiral centers, and this is introduced by these three gentlemen. These rules are called as CIP rules. This is because of their names, Kahn, Ingold, Prelog. Right? It's called as CIP rules. So R stands for rectus, that is right. S stands for sinister, that is left. It's like you are driving, and if you turn the wheel to the right, it's R. If you turn the wheel to the left, it's L, and I will come to this. And this wheel, where to turn, is decided by the sequence rule, which are decided by or given by these three gentlemen, Kahn, Ingold, Prelog. This is a picture taken in 1966. There's a Prelog here, and Kahn and Ingold. And so these are the sequence rules. So please remember what we do. We take a molecule and then we start looking at the substituents, right? And we denote ligands of a chiral center A, B, C, D in a priority sequence. And then from highest to lower sequence, we number them. And then the lowest ranking we keep away from us. The lowest ranking one we keep away, like this flower I will hold. And then I will see if it is A, B, C, then it is going to turn to the right. If it is A, B, C, then it will turn to the left. So please keep your pen and pencil ready. I'm going to ask you some questions, sir, because these are the simple questions and I would expect you to answer. So what we do, first we decide the priority and then we go from A to B to C. So from A to B to C, it will be counterclockwise, so it is S. And if it is like this, A to B to C, it is clockwise, so it will be R. These are the sequence rules, right? So you have the first one, you can ignore now. This is only for compounds which does not have chiral center, but they are still chiral. So zeroth rule, you can ignore now. I will repeat it later on. And the rule is simple, the near end. So one of the example of such a compound is allene. You can look at my video. And allene is such a compound which is not chiral. But the moment you put substituent, it becomes chiral. It doesn't have a chiral center, but still it becomes chiral compound. All right. Now, here what we do, so first one we can ignore now. Let's go to the second. What we do, based on the atomic number, we decide what is highest priority. So if you have a higher atomic number, it gets higher priority. Now, if both of them, they have same atomic number, then we look at atomic mass. For example, in case of hydrogen or deuterium or tritium, you have the same atomic number, but atomic mass is different. For tritium, it's 3, for deuterium, it's 2, hydrogen is 1. So this way we go. Second, your cis is higher than Z or trans. Z is higher than E. Cis is more than trans. Z is more than E. Like pairs, RR and SS precedes unlike pairs, and R precedes S. So these are the rules. Basically, I would say just remember first two rules. They are more important. Okay, and then you should also, for complicated problems in the competitive exams such as CSIR, you also need to know these rules 3, 4, and 5. All right. So let us look at this. So if I want to give priority, my I, because it has a higher atomic number, it will get 1, bromine 2, carbon 3, hydrogen 4. Once I decide the priority, I know that I'm going to move, like keep this H away from me, and this will be rectus or R because it goes clockwise. And exception is that if you have a lone pair, the lone pair gets lowest priority. Now, if the same priority at the first carbon, let's say if all of them are carbon, then we have to go to the second point of difference. So let me give you a few examples, and it's like Kaun Banega Crorepati. I want fastest finger first. So please be ready. I'm going to ask you some questions. And these are simple. Can you tell me which one gets higher priority between the two? 1 or 2? Which one gets higher priority? You can type your answer as 1 or 2. 2. Okay, and that's Thora, Dipali, that's correct. And why? It is because, you see, it is because this is same, CH2, carbon is same. But here, carbon is connected to H, and C. Here, carbon is connected to carbon, and H. Therefore, this gets higher priority, not ethane. What about this? 1 or 2? 2, correct. Yeah, even if you give wrong answer, it is just fine. You just try. Now here, why Priyanka is thinking that this should get higher priority? Because she looked at the bromine. See, unless you give wrong answer, you will not know what is right. So I really appreciate you for giving the answer. See here, you looked at bromine and you thought this has to get higher priority. Remember what I said? You have to go stepwise. Go to the first point of difference. So you start from here, carbon, hydrogen, hydrogen, carbon. Here you have hydrogen, deuterium, carbon. So this gets a higher priority. You have to go stepwise. 1, 2, 3, like that. Okay, you have one more chance, Priyanka. Next question. This you saw. 1 or 2, which gets higher priority now? Absolutely right. Here you see, although you have OH here, OH is far. You have carbon, carbon, carbon. Here you have carbon, hydrogen, hydrogen. So obviously this is going to get the first priority. Okay. Now question comes when you have phantom atoms, means when you have ghost atoms. So my suggestion to you is that don't judge just like that. First you unfold it, open it. So whenever you see a double bond, you break this double bond mentally. And you write, when you break a carbon-carbon bond, you write it. So CH-CH, you put CC-CC here. Then carbon-carbon triple bond, you put CC-CC here. Now, if you have a CO, you put a CO here, we are breaking the CO bond, this becomes OC, this becomes CO. Then this C triple bond, N, you break this. This becomes CN, this becomes NC, CN, NC. And when you break it, then you will get the priority. If you just try to judge like this, you will get a wrong answer. In the exam, competitive exams especially, these are the questions that are asked. So just remember, when you are breaking a CO bond, you will get C connected here and O connected here. When you are breaking a C triple bond N, you will get an N connected here and C connected here. And then you try to judge the priority. Right. Now this brings me back to the same diagram I started with today while talking to you. So here. So this is my molecule of ethane. This is the flying wedge formula in the video, if you can. This is a sawhorse formula. If I just tilt it and I see it like this, this is my sawhorse of ethane. And when I tilt my sawhorse in this direction, I get a Newman formula. This is my Newman projection formula. And then if I want to convert it into Fisher, I'll have to first make it eclipsed. This is staggered. I would like to make it eclipse. And then I'm going to move it like this. This became my Fisher formula. Now remember, in Fisher formula, the horizontal bonds are coming towards you. The vertical bonds are going away from you. So here, these two hydrogens, this hydrogen in your slide is going away from you. Whereas the horizontal ones, They are coming towards you. This is something you should remember because many exams require you to interconvert Fischer into Newman. So, for example, this is methane. You can see basically we are representing a 3D structure into a 2D formula, right? And you have this perspective drawing. You can look from one side. This is horizontal. Push it back. And what you get 3, 4, they are coming towards you. 1, 2, they are going away from you. This you remember, then you will not go, you will not make a mistake. It's just like this. You put these two in your hand, push it back. Then you know that these two are horizontal coming towards you. These two are going away from you. Here is the mistake. Only here we can make a mistake and then the configuration changes. Now you can directly write R or S in Fischer. Okay. Let me give you an example. So if you have, but before that, there are some rules of Fischer projection. Okay. You can interchange. You can interchange this atom horizontal into vertical, but you have to do 2 at a time. Okay. 2 pairs. You cannot just do 1 because if you do 1, then 1 pair exchange, then you get the enantiomer. Right? You can interchange, but you have to do it twice. And also you cannot rotate by 90 degrees. You can only rotate by 180 degrees. This is because when you change to 90 degrees, that's the other enantiomer. Because what is horizontal now will become vertical. And vertical means it is going back. So it will change everything. Okay, this is how we interchange. So we start from ethane, Fischer formula. When you, so this is my, you can look at the video now. This is my Fischer formula of ethane. And if I rotate it like this, it becomes my flying wedge sawhorse. And then it becomes my Newman. This is my eclipse Newman. This is my staggered Newman. I think it is clear. Are there any questions so far? No. Now, number of chiral centers. We say that maximum number of isomer is 2 raised to n, where n is a number of stereo element. Then these total number of stereoisomers can be diastereomers, can be enantiomers, or can be mesoisomers. Now, what are the meaning of these words? So enantiomers have opposite configuration at each corresponding chiral center. So when you look at D-glucose and L-glucose, all the chiral centers are opposite, not just one. And diastereomers, they have some matching, some opposite configuration. So when you compare glucose with mannose, only C2 is different. And therefore they are diastereomers, not enantiomers. And meso compound, just remember it has an internal plane. And due to the internal plane, there's an internal compensation and molecule doesn't remain chiral, it becomes achiral. Now that brings me to the last point of discussion for today. And I think we are pretty much in time. I will need 5 or 10 minutes max. So require your attention here. This is slightly tough. So these molecules are chiral without having chiral centers. For example, this BiNAP, and this BiNAP has a great implication in asymmetric synthesis. BiNAP comes from this naphthyl, bi-naphthyl groups. Now, BiNAP on its own is not chiral, but the moment you put this big substituent like diphenylphosphine here, there will be a hindrance for rotation. It will not be able to rotate because these groups will hit each other. And due to the steric hindrance, rotation is not possible. It's a fixed rotation, just like a double bond. And therefore, you get 2 different type of isomers here, R-BiNAP and S-BiNAP. These molecules, they do not have any chiral center, but they are still chiral. This is because their mirror image is non-superimposable on each other. You can see their mirror image is not superimposable. All right, so they don't need, for chiral compound like methane or carbon having chiral center, we need 4 different substituents. But for axial chirality, you don't need 4, you just need 2 substituents. For example, here, this is one substituent on this side, this is other substituent on this side. Right. So here are the examples. So if you have a COOH and nitro hooked up to biphenyl, right? Then these two compounds are mirror images which are non-superimposable of each other. And therefore, here is the axis of chirality. We call it has a chiral axis. All right. And I can give you an example of allene. So allene, as you can see, you can look at your camera video now. So you have one, the central atom is sp carbon, and these two are sp2. All right. And the molecule is like this. So you have one double bond overlapping and the other double bond overlapping here. It looks like this. So the central carbon is sp hybrid. So allene on its own is not chiral, but the moment you put different substitute like methyl and hydrogen, this becomes chiral. You can do it yourself. You can check the mirror image. This is a mirror image. And when you try to overlap here, your H will overlap with methyl. Your methyl will overlap with H. So it is not non-superimposable mirror image. Now, what are the symmetry elements in allene? Allene, do you see a plane of symmetry? Is there any mirror? Yes, no. In this compound, do you see plane of symmetry? Yes, no, plane of symmetry. Can you divide this molecule into half exactly? No, correct. So it doesn't have inversion axis, it doesn't have plane of symmetry, but it has only C2. And therefore, how it is C2? It is very difficult to get allene C2, and this rectangular box helps you. So this is allene, how it is. Now, if you imagine this axis, the vertical axis, and you rotate it by 180 degrees, this atom goes here, and this atom goes here. So the corner atom gets exchanged. So this is one C2 axis, this is another C2 axis, and this is another C2 axis. So allene has 3 C2 axes, and only C2 axis. So that keeps it chiral. Okay, it is not a chiral if you have a methyl group. So these are the 3 C2 axis of symmetry in allene. Okay, there are more examples of axial chirality. You can see what is axial chirality? Molecule which lacks stereocenter, but they are chiral. So you can see here, right? This is vertical, this is horizontal. And this is called as alkylidine cyclohexane. This is actually chiral. This is the axis of chirality. This is adamantane. This is axis of chirality. This is styrene, axis of chirality. So if you just have 2 substituents, it's good enough to make them chiral. So far what we talked about is we talked about isomers, where we have different molecules with same molecular formula. Then we look at the bonding connectivity. If the connectivity is not same, they are constitutional isomer. If the connectivity is same, they are stereoisomers. In stereoisomers, we have enantiomers and diastereomers. And then we also have in enantiomers meso compounds. They have the plane of symmetry in the molecules. So this is our entire spectrum of chiral molecules. So this is what we learned today, and I have completed my lecture in 45 minutes, and we are right on time. So this is what we learned today, right? I did not touch upon how do you study the configuration of atropisomerism, how do you calculate R and S. If you're interested, I can send you a PDF file for this. All right, so I stop here, and please feel free. I would like to know if there are any questions on what we discussed today. Hope this is useful, and if you can tell me if you have questions, I'll be happy to answer.
जर कोणाला काही क्वेश्चन असतील तर अनम्यूट करून तुम्ही बोलू शकता.
Yes, you can do that too. Okay, looks like there are no questions. So without, looks like there are no questions. So let me once again thank the organizers for inviting me and giving me the opportunity to share my thoughts on stereochemistry with you. And I sincerely hope that some of the parts will be useful to all of you. Thank you.
Thank you very much, sir.
Thank you.
So, on behalf of Department of Chemistry and Royal Society of Chemistry, I convey my thanks to Honorable Professor Dr. Suvarna Kulkarni, sir, that he took the initiative to arrange this beautiful lecture series for our student. It's only because of you, sir, that our student can listen or attain the very informative lectures on various topics of chemistry subject. So really, it's a very magical and unbelievable situation to our student that to attend the lectures from highly recognized person like you. So once again, thank you very much, sir. So in your talk, sir, you give basic information. I know that really that the stereochemistry subject is a little bit complex one, but your talk is very beautiful and very informative. That the lot of the things like the chirality, so once again, thank you very much to be present with all of the students and take some like initiative to arrange this kind of series. Thank you very much, sir.
Thank you.
I would like to thank also our in charge principal, Dr. Haraj, that for his constant support. I also thanks to our departmental head, Dr. This series. Thank you very much, sir. Now over to the Kirti madam.
कुलकर्णी सर खूप खूप आभार. आपण
नमस्कार सर. आणि या सगळ्याला
Thank you, sir.
कारणीभूत असलेला माणूस तो तिथे हसतोय, रोहित.
हो.
Hello,
Yes,
sir.
sir. Yes, sir.
रोहित, एकदा we will go once to Ratnagiri.
Sure, sir. Sure,
या सर या नक्की या सर.
Okay. Okay, over to you, Rohit. I don't want to take more time. Thank you so much.
Thank you, sir.
Thank you, sir. Thank you.
Okay,
Thank you.
thanks.
Thank you, sir.
Thank you.
Now we are entering into second technical session of today, which is on organometallic chemistry. Now I request Dr. G.B. Pawar, sir, to introduce our speaker, Dr. Rohit Singh Chauhan, sir, to our audience.
Okay, sir. Good morning, everyone. It gives me immense pleasure to introduce today's speaker, Dr. Rohit Singh Chauhan, sir. Welcome, sir. Warm welcome to this session. Dr. Rohit Singh Chauhan, sir, has done his master's from Christ Church PG College, Kanpur in 2007 and got selected to HBNI PhD program. Under this program, he has undergone 1 year rigorous work for a BARC training school and joined chemistry division to pursue his doctoral study. He was awarded PhD degree from Bhabha Atomic Research Center, Mumbai, under the aegis of Homi Bhabha National Institute, Deemed University in 2013. Later on, he moved to École Polytechnique, Paris, to pursue his postdoctoral work. His research interest covers the synthetic inorganic chemistry, organometallics, and catalysis. At present, he is working as capacity of Dean, Research and Development at KJ Somaiya College of Science and Commerce, Mumbai University, and teaching undergraduate and postgraduate students. He is having several international peer-reviewed articles book chapters and books to his credit and awarded prestigious Dr. S.K. Somaya Award for Excellence in Research, Higher and Technical Education in 2019. So, dear participants, please tighten your seat belts and be ready for this enlightened speech. So, now I am requesting Dr. Rohit Singh Chauhan sir to deliver his lecture on the topic Electronic Spectra of Transition Metal Complexes. Thank you. Thank you, everyone.
Am I audible?
Yes, sir.
Yeah, okay. So thank you, Dr. Ganesh, for the kind introductions. At the outset, I must congratulate to Aba Saheb Marathe College, Rate Shikshan Sanstha, for organizing this lecture series. I must congratulate to Principal Dr. Ghanshyam Hawale, who has taken a pain to organize this lecture series, along with the Head of Department Chemistry, Dr. Hemant Akolkar. So today I am going to discuss about the electronic spectra of transition metal complexes. See, dear students, if I must say quantitatively in every examinations, you will realize that 25 to 30 questions used to become from this particular part. Sometime we might not be familiar that whether the answer are coming from electronic spectra or metal carbonyl. So today I will discuss about some basic logic, and parallelly I will solve some questions which has been asked in NET, JAM and GATE examinations. So the most fascinating part of the transition metal chemistry is the color, and the color is basically related to the electronic spectra. So how does its electronic spectra originate? That's the main thing. So if you will see here, when a beam of monochromatic light is passed through a sample, the part of the energy of the light is going to be absorbed, and as a consequence, the electrons are going to be promoted from lower to higher energy level. Again, I will repeat, when a beam of monochromatic light is passed through a sample, a part of the light is going to be absorbed, and as a consequence, the electrons of lower energy level are going to be promoted to higher energy level. Now remember, the energy which is associated with the transitions of lower to higher energy level of electron, that play a crucial role to define the various property of the transition metal complexes. Okay, so this is the electron of lower energy level. After absorption of particular frequency, the electrons get promoted to higher energy. Now see, this delta E play a significant role to define the various property. Okay, now second thing which is important in electronic spectra is called as complementary color theory. What does it correspond to? It simply corresponds when you are passing, when your sample is absorbing a particular wavelength of light, remember that the complementary color is going to be observed. For example, suppose your complex is absorbing a red color of light, then in appearance it will show the green color. Okay, so this is called complementary color theory. To different prospect, first, after the absorption of light, the electrons are going to be promoted from lower to higher energy level, and this delta E is crucial to define the color and other properties. Secondly, after the absorption of particular wavelength of light, always remember the complementary color is going to be observed. Now let us take one question which has been asked in GATE. Match the following compound with their color. So in the left hand side, I have mentioned three complexes: Fe, NH3 + 2, iron aqueous, and hexachloronickel chloride, and their color. So what you have to do, you have to correspond the color of these complexes. Now how to solve these questions? See, in coordination compound, always remember your first strategy to look around the ligand system. Okay, so first thing is that you need to write down the complementary color. So like for red, the complementary color will be green. For blue, it will be orange. For yellow, it is violet. Then the next job is to arrange the ligand in the increasing order of field strength. So here, three different ligands are there: ammonia, water, and chlorine. So let us first arrange them in the increasing order of field strength. So this is ammonia, then water, then Cl. Okay. Then why we are arranging this? Always remember, the field strength defines the splitting of energy. If the field strength will be more, splitting will be more, and in that case, delta E will be more and lambda will be lesser. Okay. The moment splitting of D energy level is going to be more, what basically it connects to, delta E is going to be more. So in short, lower wavelength of light is going to be absorbed by the sample. Okay. So first we need to arrange the ligand in the increasing order of field strength. So in our case, it is ammonia, then water, then Cl. Then now you need to write down the energy order, or you can say the lower wavelength of light. So violet, then green, then orange, right? That complementary, you see that? Violet, green, and orange. Since violet is of lower wavelength, higher energy, so it means that it is connected to ammonia, right? And water is connected to green and Cl is connected to orange. But don't be get confused. Here we have written it with respect to the complementary color. Their absorption will be their complementary. It is red, blue, and yellow. So with respect to violet connected to ammonia, what will be the appearance? Of course, the complementary. Violet ka complementary, it's a yellow. So for FeNO3 6, the appearance will be yellow. Next, water absorption is green. So complementary color is going to be red. So we have to connect it with the red. And the last one is NiCl6. So in that case, absorption is orange. So with respect to the orange, the appearance will be of blue color, right? So this way we can correlate the color of the complexes. Again, I will repeat it. Whenever any question has been asked to connect with the color, your first job is to write down the complementary color of the mentioned table, right? Second, you need to write down or arrange the ligand in the increasing order of field strength, right? And then you need to connect those ligand with respect to the absorption of color or lower wavelength of light. Okay? And then you can write down the complementary and connect the complementary. Okay? So this question has been asked in GATE. Now the next is type of electronic transitions. Okay. So overall, there are 4 electronic transitions are possible. First is called intrametal. Second is called charge transfer. Third is called intraligand, and fourth is called counter ion spectrum. Okay. So in case of intrametal transition, as the name suggests, these are the transition in which the transition do occur within the metal. Since we are talking about the transition metal, so in this case, the electrons are going to be promoted within the d orbital. That's why we are calling it as intrametal. And these type of transitions are popularly known as DD transitions. Okay. Second, charge transfer transitions. So in this case, there will be a redistribution of electron density between metal to ligand or ligand to metal. Depending upon the flow of electron density, we have further been classified this charge transfer transition into 2 types. I will discuss it little later with detail. So as if now, what is charge transfer transitions? If there will be a redistribution of electron density between metal and ligand or ligand to metal, those transitions will be called as charge transfer transitions. Again, intra-ligand transition. See, in chemistry, wherever you will see this word intra and inter, make a note that intra means within and inter means outside, right? So intraligand means if the transitions are the flow of electron involved in between of the 2 ligands, then in that case, those transitions will be called as intraligand transitions. I hope it will be very much clear. Intrametal within the metal or within the d orbital. That's why it is called as DD transitions. Okay. The next is counter ion spectrum. See, the ligands which are present outside the primary coordination sphere, those will also participate in some of the cases to the flow of electron, and that's why those transitions are called as counter ion spectrum. I have written the example also. For example, in case of intrametal, for example, it is hexaaqua titanium complex, right? And for intraligand, it is rhenium, tricovalent X, and then 4th one. Okay. Now see here, intraligand. Because of this amine group, you see that how many type of colors do appear. right? Now let us discuss about more prominent transition that is called charge transfer transitions. Just now I told that the electron can be flow from either from metal to ligand or ligand to metal. Depending upon the flow, they had been categorized into two categories. One is called metal to ligand and another is called ligand to metal. So it is very clear, if there will be a flow of electron from ligand to metal, then those transitions will be called as LMCT, ligand to metal charge transfer. And suppose the flow of electrons are going to be occur from metal to ligand, then those will be called as metal to ligand charge transfer. See, for LMCT, the popular example is permanganate and even potassium dichromate. Okay. Now I will take one by one all these transitions. Honestly speaking, this fourth one is not very prominent, intraligand and counter ion spectra. And if you will realize, I even notice most of the time the questions do come from intrametal transitions or charge transfer transitions. Now let us solve. Let us take the intrametal transitions. So here, if you will see in the left hand side, I have shown one test tube that contain a solution of hexa-aqua titanium complex. You see that the color, right? Quite intense in nature. Titanium, it's a D1. After the absorption of energy, the electrons are going to be promoted from T2G to EG level. You see this. In the ground state, one electron is present in a T2G orbital. After absorption of energy, that electron is going to be jumped, right? So earlier in the ground state, the electronic configuration was T2G1, but in excited state, it is EG1. So in short, your electron has been promoted from lower to higher energy level. So how many transitions should be appear? Think about it. It should be one, right? Only one electrons are going to be jumped. But in practically, if you will notice, the nature of the spectra is not sharp. You see this. It's not prominent. It's not proper Gaussian, right? Some shoulders has come. You see this. Once you have recorded the UV waves of this complex, you will realize that it's not prominent sharpness, right? Now, my question is why? See, in electronic transition, first of all, you need to think there will be a promotion of electron from lower to higher energy. Then why don't it come a linear in nature? It's a coming in Gaussian. Think about it. See, the moment you are talking about the movement of electron from lower to higher, then in that case, of course, the nature of the spectra should be linear. But what you are realizing here, it's a Gaussian. Now, the question is why? I'm keeping this question open for you. And at the end of the lecture, I will take these questions and I'm expecting some answers from a student as well. So anyway, now let us come back to the point. For D1, you see, even it is a Gaussian, but it is not sharp in nature. Now the question is why? Why it is not sharp? Anyone from a student? Anyone? Why it is not sharp? I'm waiting at least one response. Okay, anyway, now think. See, in organic chemistry, there is a one concept that is called John-Taylor distortion, right? Now see here, the moment your electrons are promoting to EG. Now, how many EG orbitals are available? 2. And here I am showing that this electron is going to be promoted to ES. Agreed. But in EG, there are the 2 sets of orbitals. One is called x square y square and another is called dz square. Now think about it. One electron is having the 2 positions available to be get accommodated, right? So how can you write it? Only the electron promotions to ES. Means which ES? It is dx square y square or dz square. Of course, the 50% probability is correlated with these transitions. And that's why it doesn't come sharp. You cannot say the electrons are going to be flipped only to dx square y square. No, there is a possibility for dz square as well. Of course, the energy which is associated will be a bit higher, but probability is there. And that is called John-Taylor distortions, right? So because of John-Taylor distortion, the nature of the curve is not sharp. Okay, let us take another example. Now see about D2. Now think, First question is, in D2, how many transitions are feasible? See here, 2 electrons, ground state is T2G2. If I would ask how many possibilities are associated with D2 transitions to go to the excited state, it will become 3. How? See, first 1 electron is going to be jumped to higher. Now you see 1 electron is going to be at higher state. Second is that, now remember in EG there are the 2 orbital, one is called dx square y square and another is called dz square. Here I have shown both way. You see this. 1 electron, dx square y, this is dz square and this is dx square y square. And another is possibility is both the electrons do get jumped from lower to higher, right? So overall 3 transitions can be possible. And remember here I have mentioned that the electronic state 1 is of lower energy. So basically, suppose your electron is available in dxy orbital and it is going to be jump in dz square orbital, then it will be of lower energy as compared to dx square y square, right? Think about it. Okay, so there are 3 absorptions are possible. So if you will take the sample and record the UV waves of D2 system, you will come to know that again there will be a 2, and even you can say there will be an appearance of solder, right? Since the energy is too close, that's why the sharp appearance don't come in the UV waves. Okay, now I'm leaving the rest of the configurations like D3, D4, D5, D6. You do it as a homework at your level, right? Let us move ahead now. I will take on some questions. For example, this is a question: copper orthophenanthroline complex ion is colored due to. Now, what will be the answer? I told you all the 4 transitions, even how the electronic transitions do occur. Now, this question has asked that copper orthophenanthroline 3+2 ion is colored due to. Anyone? I'm waiting. Now see, again, I told you, just now I told you that whenever you get confused, always think about the ligand. Always think about the ligand. Now here, orthophenanthroline, it's a chelating ligand, right? Getting coordinated to copper, right? So in this case, remember the nature of the transition will be metal to ligand. Okay, it will be MLCT. Next, FeCN6 3- is colored because of. It's a very popular question actually. If you will realize the color of the compound is blue, I'm telling you. Why it is so? Why it is so? No answers. No. Anyway, okay. So the answer will be DD transitions, and even the more appropriate answer is intervalence transitions. Because in case of potassium ferroferricyanide, iron exists in the 2 different oxidation states. One is a Fe+2 and another is Fe+3. So the moment electrons are going to be involved in between of these 2 oxidation states of the same metal, then in that case, the more appropriate answer will be intervalence transitions. Otherwise, it's a DD transitions. Third, orange-red appearance of bismuth triiodide is caused due to. Now, these are the options. Again, try to concentrate on the ligand system. Here, the anionic ligand is iodide, which is quite bulkier in nature. So most of the cases, wherever iodide is involved, be careful. In that case, the flow of electron will be ligand to metal charge. Okay? Yes. Okay, now I will take one by one. Ligand to metal charge transfer. Now see, here I have drawn the ligand orbital of lower energy and then metal orbital. So LMCT, the flow of electron from ligand to metal. Now, once the electron is going to be flow, right? Ligand will become up and metal is going to be little lower, right? Achha. I will try to connect this type of transitions with your practical life. See, ligand is going to provide the electron to metal, right? Just think, suppose you are having 2 friends. One friend is having a money and another friend is struggling to get vada pav, I must say. Now, You tell me one thing, that what property is required to your friend to get the money from you? Just think about it, right? See, first of all, since you are having a money, so you will have an attitude. But whether your friend is showing the attitude and you are going to give the money, no. Am I right or wrong? See, I need a money, right? In that case, I have to ask that, please help me, I need a money, right? So my energy should be up low. And since you are giving to money, so it is like, no, I'm having a money. So attitude matters, right? So always remember, energy is going to be low. Now see the properties. So ligand, low electronegativity. See, electron can be correlated with the money, right? See, you can give the money only if you are not too much greedy, right? Okay, like if some friend is required only 2 rupees, then you will say, okay, I'm having a 12, so I will give it. So it is of low electronegativity, and low electronegativity should be present in ligand. Why? Because ligand is providing the electron. Suppose if it will be reverse, then see, in case of reverse phenomena, what would be happen? You will not give the money, then there will be a no flow of electron, right? So always remember, for to happen the ligand to metal charge transfer, there should be a low electronegativity of ligand. Secondly, the moment it will provide the electron, it will be get oxidized, so it should be easily oxidized. And third, money means you should have a filled orbital of, okay. Now with respect to metal, what are the characteristics are required? See, first of all, it should be of lower principal quantum number. Second, it should have higher oxidation state. See, higher oxidation state means there should be empty pocket available to get the money and keep it inside. Are you getting my point? See, if you are not having a space, where will you keep it? That's why I told you that in case of metal, there should be higher oxidation state. The moment higher oxidation state means there are the orbitals which are available to accommodate the electron. And since metal is in a needy, so metal has to be an orbital which can accommodate the electrons are provided by ligand. So metal should have higher oxidation state. Third, the vacant orbital of lower energy. Now see, from this two particular part, how many properties are going to be connected, I will show you. Now see, the moment LMCT will be more, pi bonding will be more. If the pi bonding will be more, then bond order will be more. And if the bond order will be more, then bond strength will be more. And if the bond strength will be more, then bond length will be lesser. And if the bond length will be lesser, then bond energy will be more. And the last one is mu ml will be more. Right? Now see how many properties are correlated with LMCT. Again, I will tell you. If the LMCT will be more, then pi bonding will be more. Pi bonding will be more, then bond order will be more. If the bond order will be more, then bond strength will be more. And if bond strength will be more, then in that case, bond length will be lower and bond energy will be more and mu ml will be more. So altogether, only one property, that is bond length, is going to be decreased with the extent of increasement in ligand to metal charge transfer. Clear? Okay. Now, let us take some questions. Arrange the following in the order of higher extent of pi bonding. Now see, this question has not asked directly from LMCT. Now they are asking pi bonding, but the answer is going to become from electronic transitions. So these are the cases, aminophore, actinium, and rhenium. Now see, how do we solve? First of all, you need to see that which type of transitions are occur in this case. So it is LMCT, right? Now, as I told you that whenever you will start solving any questions related to the electronic transition, first priority you should give it to ligand system. Now here in all the three cases, basically ligand is same. Only the metal is going to be changed. In one case it is manganese, in the second case it is titanium, and in the third case it is rhenium. Now see. So the variable is metal. Now we have to think about the properties which is required in case of metal for LMCT. So if you will remember, in that case, I told you that it should be of higher oxidation state. Then second thing is that it should be of lower principal quantum number. Okay, since they do belong to the same series, magnesium, titanium, rhenium. Magnesium is coming in 3D, titanium is coming in 4D, and rhenium is coming in 5D. if you want to solve the oxidation state in all the cases, the oxidation state is same. So you are not going to get the answer from the oxidation state. The next is the low principal quantum number will be of higher LMCT, right? So now see, in this case, it belongs to 3D. So principal quantum number is 3. For tactinium, principal quantum number is 4. For rhenium, principal quantum number is 5. So what would be the order? At least now you should respond. What would be the order? Of course, it will be 1, then 2, then 3. So manganese will have more LMCT or more pi bonding as compared to tactinium and as compared to rhenium. That is straightforward. Okay, let us take one more question. Same. Vanadium, chromium, and manganese. Again, now, as I told you, first to think about ligand, but again, the ligand is same. Now, what are the things which are going to be varying? Is only thing is metal. Now see, in the first case it is vanadium, then chromium, then manganese. Now again, metal is going to be varying. Now metal, 3 properties: oxidation state, low principal quantum number, and of low energy, right? Now see, all 3 belongs to 3D series. So now low principal quantum number can be excluded. The only availability is now the oxidation state. So in this case, you have to calculate the oxidation state of central metal, right? Like here it is 7, it is 6, and it is 5, right? So higher oxidation state favorable. Why? Because I told you, if the metal will have higher oxidation state, what does it correspond? It corresponds that it is having an empty pocket available. Pocket means orbital. And why it is required? Where it will keep the electron. It needs a space, no? That's why I told you higher oxidation state is more favorable. So the answer will be 3, 2, 1. Okay, next. Arrange the following complexes in the increasing order of their energy required for the transition. So these are the cases. Now see, in all the 3, central metal is fixed, and that is cobalt. And there are the 2 different type of ligand. One is ammonia, and second is halogen, right? Ammonia is also constant. Only variable available is halogen. So in one case it is chloro, fluoro, and bromo. If you will remember, just I think a few slides ahead, I had showed you that in case of bismuth iodide, it is LMC. And I told you iodide means bulkier anions. It is having a rich in terms of electrons. So what it will do? It will provide the electron, right? And in case of ligand, I told you the ligand should be of low electronegativity, right? Why it is low electronegativity? See, if it will be of higher electronegativity, basically it is greedy, no? So it will not give the electron. So in this case, if you will see, the order will be 3, then 1, then 2. Okay. Now let us move ahead and discuss about metal to ligand class. Same diagram, only I have switched or flipped the orders. So here the electrons are going to be provided from metal to ligand. After the transitions do occur, what the changes are going to be happen in metal orbital and ligand orbital, let us discuss about. Remember, whichever is going to give the electron, or it simple means it is rich, right? So whatever the property a rich person will have, same thing we can connect it. Now let us discuss about it. Now see, since metal is providing the electron, so of course it should have low oxidation state, so that it should have an electron first of all, right? Second point, it should have a filled orbital of higher energy, and the third, higher principal quantum number. Now here ligand is needy. So needy should always have empty orbital available, or you can say the pocket should be available to accommodate the money, right? So in this case, there should be an empty orbital of lower energy, and it should always be ready to take the electron. So in short, I can say it should be easily reducible and of higher electronic. Okay, so these are the properties which are connected with the ligand orbital in case of metal to ligand charge transfer, right? Up, what are the other properties which can be connected with this MLCT? Again, I will tell you, you see this. If MLCT, MLCT will be more, pi bonding will be more, then bond order will be more, then bond strength will be more. Only again, bond length is the only parameter which is having an inverse relation. Okay. Since I have discussed in detail about the LMCT, so I will not take much time about it. So the best example is metal carbonyl complexes. See, we get confused that metal carbonyl is a separate part. You see, the metal carbonyl is also come from metal to ligand. Here I have shown the pi bonding. So first there will be a flow of electron from CO. See, one important question is, in case of metal carbonyl, always remember the electrons are going to be flow from ligand to metal, and that to a hybrid orbital of CO. Always remember, it's a hybrid orbital of CO. And it will be accommodated in the empty d orbital. So first they will make a sigma bond, and then the metal is going to transfer the electron. You see this. Okay? Now, let us solve some questions. Arrange the following in the increasing order of back pi bonding. So these are the examples. Now here, metal is also same and ligand is also same. The only variable you can notice is the oxidation state. So in the first case, the oxidation state is -1. Here it is 0. And here it is +1. And here it is +2. Now see, since it is MLCT, so metal should be rich. So metal can be rich only when it should be have lower oxidation state. So the moment I said metal is having a -1 oxidation state, it means it is having more electron. So of course, the here MLCT will be more for MCO6 -1, then with second, then third, then fourth. So see what is the answer? So answer is 1, 2, 3, and 4. Okay. Second questions. If you want to write it with respect to the energy of radiations, then it will be reverse. Okay. Now, yeah, again, this is a question. Which transitions in LMCT may be responsible to impart the color in octahedral complex? These are the options. Now, this seems quite tedious, no? Because in this case, MOT is involved. Now, how do you know that which transfer is related to the responsible for imparting the color? See, color, the moment I said color, it should be of lower wavelength, right? Now see, part of the MOT I have drawn it here. So these are the sigma LGO, are ligand group orbitals which are involved for the sigma bond. What is pi LGO? Pi LGO is the ligand group orbital which are involved for the pi bond formations. And these are the T2G and EG star. Now see, if I would ask how many transitions are possible? So of course, from sigma LGO to T2G, 1, and sigma LGO to EG star, right? What are others 2? One is pi LGO to T2G, and fourth one is pi LGO to EG star. So overall, these 4 transitions are possible in case of octahedral complexes. And since it is LMCT, so of course, the ligand orbital will be of lower energy. Now think, if you will compare, or if I will ask that which transition is associated with the lower energy, what will be your answer? You think these 4, 1, 2, 3, 4. Which one will be of lower energy? Of course, this fourth one, pi LGO to T2G. So this is the transition which is responsible to impart the color in LMCT in octahedral complexes. Suppose the same question will be asked with respect to MLCT. Now what will be the answer? I have already written here. See, so in case of MLCT, what would be happen? This diagram is going to be reversed. Why? Because now metal is the donor and ligand is your receiver zone. So these orbitals which you have mentioned, sigma LGO and pi LGO, they will be of higher energy and metal will become lower, right? So in that case, remember EG star to pi LGO will be of lower energy. You try it and you will come to know the answers. Okay. Okay, let us move ahead about the transitions. The next job is microstate. So if you will remember in your 10th standard, if your teacher will say, write down the electronic configuration of P2, right? only the information has been provided to you, P2. So what is the normal trend? What is the normal trend? If I will ask, write down the all possible transitions of P2, right? At 10th standard, what do you write? Even at this level also you will write. See, the moment I said P2, I'm pretty sure that you will only write this two. Right? One orbital in PZ and another orbital is Py. Now my question is, suppose one of your friend has drawn the P2 in this way, and he has kept the electron in Px and Py. Right? See, the information is given P2. And the question is asking that write down the P2 configurations, right? If you remember at 10th or even 12th, P2 means like this way, 2 electrons in first 2 orbital, right? Now my question is, why we cannot write the filling of electron in the last 2 orbital? Or another possibility is also exists where one can draw the electron in first orbital and another electron in the third orbital. What's wrong in that? See, in chemistry, there are the 2 basic principles. One is the Pauli exclusion and second is Hund's rule. Actually, these 2 rules should never be violated. And if you realize, these rules are not going to be violated in any of these 3, right? Agreed or not? See, the information is given P2. Now I'm having a full freedom to fill these electrons in any set of possible way. The only thing is that Hund's and Pauli should not be violated. Now see, I have drawn it 3, even there will be a more possibilities. Why the remaining 2 always kept aside like these are wrong? No, it is not wrong. You see, the information is P2. So you have to fill 2 electrons in a p orbital. And the basic thing is that you should not violate the Pauli and you should not violate the Hund's. In any of the cases, if you realize that I have not overcome any of these basic rules of chemistry, right? Then remember that, of course, these 3 are also right. Right? And these are called as microstate. Now see, the question was P2, right? The question was P2. So now if I want, I can write it. I will delete it first. So P2 I can write N is equal to 2, L is equal to 1, ML will be -1, 0, +1. And MS will be either +½ or -½. Right? Here you see this third one. I have drawn where I have accommodated both the electrons which are having an opposite spin in the same orbital. See, this is also right. Why? See, again, the question is P2. What information is given? P2. I have followed the basic principle of Pauli's, right? So remember to write any of the configurations. There are the ways, right? And these ways are having different. And of course, if you will ask to me with respect to this, in this case, energy will be more. That's okay, but you have never discussed about the energy, right? So the arrangement of these configurations with respect to the energy is called as the microstate, right? See, I have written here with the red, these configurations are called as microstate. Don't mug up the concept. My basic thing is, don't mug up the concept. Just try to connect and think why it is happening. That's it. That's sufficient to understand the chemistry. It's a very good subject, right? The only thing you have to evolve the logic and reasoning, right? Just now I told you, when I was in the 10th, I do know that for P2, we have to accommodate the 2 electron in the 2 first orbital. That's it. But it's wrong. See, it is right, but another fellow who is filling the electron in the same orbital, that is also right. Right? And these arrangement of configurations with respect to the energy is called as microstate. Okay? Now, of course, they do have a different energy. That is a different set. We will discuss it. Now, for any configuration, how do we calculate the number of microstate possible in any configuration? So the formula is n factorial divided by r factorial multiplied by n minus r factorial. I hope you might be quite familiar with this. So here n is the twice number of electron, or you can say the maximum number of electron can be filled in a given orbital. For example, in case of p, the maximum electron can be filled is 6. And what is r? R is the number of electron for which you are looking for the microstate. For example, here it is P2. So the value of R will be 2, right? So in case of P2, if you will see, the total possible microstate will be 15. Just think, I have drawn only 4. Still 11 more are possible in case of P2. Don't you think it's quite interesting? It's a fascinating, no? Means whatever you have learned, it is something different. P2. For P2, the possible microstate is 15. First of all, try to understand what is microstate. So microstate is the arrangement of electron in the different configuration depending upon their energy. One thing. And assigning of the microstate is term. And within the term, if you are write down their lower values, then it is called term symbol. So these three things are quite connected. Let us take one by one. First, I will discuss about microstate. Again and again, I am repeating, don't mug up the concept. Try to understand what is microstate. Okay. Now, let us discuss some more for D1. So in case of D1, if you will see, I will first clear the screen actually. So in case of D1, you can directly put your formula, that is n factorial divided by r factorial multiplied by n minus r. So in this case, if you will follow the formula for D1, it is L is equal to 2, M will be minus L to plus L. So it is minus 2 to plus 2. And spin quantum number will be either plus half or minus half. So the total possible microstates for D1 will be 10. Okay. Now see, in what way these 10 microstate are possible? I have drawn it here. See, I have filled one electron in each orbital of d sets. Right? Plus 2, plus 1, 0, minus 1, minus 2. Now here, if you will see, the value of S is plus half. Again, I can revert it, no? So now the value of S is going to be minus half. So these are the 10 possible way to fill the one electron in d set of orbital, and these are called as microstate. And the whole arrangement or this diagram, what you are showing, it is called pigeonhole diagram. What do you call? Pigeonhole diagram. Clear hai? Now, and the arrangement of the microstate with respect to their energy is called as tau. Now see, since so many things are going on, so don't get confused. Right now, we are talking about microstate. We are talking about term. It simple means we are here. Don't get confused with this particular part. Right? We are on the free ion condition right now. Is it okay? Now think. So in case of D1, there are the 10 possibility, right? And the term will be 2D. I will tell you that how do we calculate the term. But as if now, just remember for D1 configurations, the term will be 2D. Now, this is the pigeonhole diagram, and these are the quantum numbers for all possible configurations of D1. I have written it here, right? So till here, all the S is having plus half, and for downward it is minus half, and the ML value is going, L value is going to be vary from plus 2 to minus 2. Okay, so this is to how to calculate the term. Okay, just wait, I will put it in more detail. Now we will take some case of D2. Just think how the things are going to be complicated. Now 2 electrons are present in a d orbital. How many possibilities you see? Put the formula, and if you will find out the total number of microstate possible in case of D2 transitions are 45. How many? It's a 45. right? Now see, in this case, if you notice, the value is going to be -2, -1, 0, +1, right? Now, what you need to do, you have to calculate the total angular momentum, capital L. And in what way can you calculate? You need to fill the electron in an orbital, multiply with the ml value and add it, right? So for term symbol, if capital L value is coming 0, then you have to assign S. If it is 1, then you need to assign it as P. And suppose if it is 2, then in that case, it is D, F, G, and so on. So depending upon the value of L, you can assign the term. Okay, now see, here you realize that I have kept it both the electrons in a same orbital. So if you will calculate it, the L, what will be the value? So here the ml is +2. And how many electrons are there? 2. So 2 multiplied by 2, it is 4. So overall it is 4. So with respect to 4, what symbol you are going to use it? It is going to be G. Right? On the left hand side, you need to write down the spin multiplicity. And spin multiplicity is calculated with 2s plus 1. So where s is the total spin. So in this case, if you will calculate the spin, so this electron will be have +½ and this electron will be have -½ So overall it is going to be 0. So it will be 2s plus 1. If you will put it value s is equal to 0, so what you will get? 1. So what will be the term symbol for this particular state? It will be 1g. Like this way you can calculate for every possible state. Okay, I will take one more. For example, let us take this one, right? Now here, one electron having +2. So 2 multiplied by 1 plus 1 multiplied by 0. So again, the overall value will come 2. So with respect to 2, what is the term symbol? It is D, right? And these 2 electrons are having opposite spin. So S will be 0. So multiplicity will be 1. So what you can write the term for this particular state, it will be 1D, right? So you can write the term for every possible state. Okay. Okay. 1G. And for this, I have solved it. It is 3F. Okay. Now, this is the pigeonhole diagram for D2. I told you that the total possible microstate is 45. You think this is pigeonhole diagram where I have tried to draw all 45 possibilities. It's a good homework to think about it, right? Next, now let us discuss one by one the term for every possible configurations. Since I am having a time limitation, so I may not be able to solve all, but I will try to take 1 or 2 so that you should have a good picture how to calculate the term. Okay, so for this, it is D1. Value of L is 2. So 2 multiplied by 1. So with respect to 2, the term is D. So we will write D. And in the left hand side, what we will write? We will write the spin state. So it is 2s plus 1. So 2 multiplied by half plus 1. So overall it will come 2. So the term symbol for this state will be 2D, right? For D2, it will be 3F. Here I am talking about the ground state. Don't get confused. Just now we have solved it for one microstate where both the electrons are accommodating in the same orbital. And if you remember for that, the term symbol has come 1G. And that is also D2. So don't get confused. For this case, the D2 is coming, for term symbol is coming 3F. It is coming because it is ground state. And that 1G is for the highest, right? Okay, so for D2, it will be 3F. For D3, it is 4F. For D4, it is 5D. Now I'm expecting an answer for D5 electronic configuration. What will be the term symbol? Students, do it quickly and tell me, what will be the term for D5? For D5, what will be the term? Quickly. I'm waiting. Anyone, you can unmute yourself and respond it. Otherwise, I will solve for you. Not able. Okay, so let us take the case D5. All 5 electrons are filled in every orbital. So overall L will be 0. You see here, overall L will be 0. And spin, if you will calculate, you need to add it. So it will become 5/2. If you will solve with the help of 2s plus 1, it will come 6. So what will be the term symbol? It is 6s. Okay. See, for full and half filled orbital configurations, always remember the term is 6 is s. Okay, not only for D5, even for D10, if you will calculate, it will come s. Even for D0, you will calculate. Actually, D0 doesn't make any sense, but still, if you want to play with D0, again, it is s. So remember my word, for half filled and full filled configurations, the ground state term will be s. Okay, and depending upon the number of electrons available, you can calculate the spin multiplicity. So this is D6, D7, D8, D9, and so on. I will not solve all the questions. I assume that you may be familiar with this. Now, okay. Now, see, it's a seems very straightforward. But the moment it comes for gate or net, the examiners are quite strict. Now, see, in what way you can calculate the micro? So there are the 5 possible methods from which you can calculate the number of microstate depending upon your questions. Till now, we are discussing about a very small thing, like for D1, you calculate the microstate. So you know the formula and you can. Now see, 5 type of questions can be asked. One, for any particular configuration, they will ask S1, P1, D1, which never to be asked in any competitive exam, to be honestly speaking. Now, suppose the electron get excited and now the electronic configuration is S1, P1, R, P1, D1, R, D1, F1, then how do you calculate? So remember, in that case, second case especially, what you have to write, you have to find out the probability for all possible configurations. So for example, Sn, you have to put this formula and then you need to multiply with another configurations and make a multiplication that will give you the complete information. Okay, it's a quite popular. Second thing is that suppose they have given you the term and now they are asking what will be the microstate. How do you calculate? So remember, in that case, you can get the answer by multiplications of 2L plus 1 multiplied by 2S plus 1. Now one more ahead, angular momentum, J is given. Then in that case, the answer will become 2J plus 1. Now suppose the splitting of orbital has been given, then in that case, see, then in that case, the answer will become from multiplicity multiplied by degeneracy. For example, for T2G, what will be the degeneracy? T means triplet. So total 3 orbitals are having a degenerate level. So 3 multiplied by 2. So the microstate possible for 2T2G will be 6. Right? So these are the 5 formulas which can be utilized for solving the question related to microstate. I will take one question. It has been asked in ISC. One of the excited state of the titanium has the electronic configuration so and so. The number of the microstate with 0 total spin for the configuration is. Tell me. You see, don't we think that microstate is too like it's too easy? You will be able to solve. Oh, it's a tricky one. Huh? You need to develop the logic. The question is there in your screen. Just think about it and let me know what will be the answer. The question is, for the excited state titanium, the electronic configuration is given. Now you have to find out the microstate which is having a total spin 0. Think. I will help you. Actually, it is for excited state. So if you will see, the last electron is basically in D1 and P1. Are you getting my point? So which formula you are going to implement? From a student, please respond. It's not too difficult. It's not difficult. You think about it. See, since we are talking about excited state, so the formula, second one is going to be applied. So it's straightforward, but be careful. Huh? The question is, you have to calculate the number of microstate with zero total spin. See, here there is nothing foundation related to the total spin. So you have to think about pigeonhole diagram. It's not straightforward. Someone has responded. The answer is 15. Okay. Vaishnavi, right? Okay, Vaishnavi, let us see that. What will be the answer? Okay. Anyone else who is having a different opinion with respect to Vaishnavi? Anyone else? Or everyone is agreed with Vaishnavi? Vaishnavi, you are wrong actually. The answer is 15. Right? I think you have also responded 15. Okay, so your answer is right. If I'm not wrong. Okay, Vaishnavi is suggesting second, Sangeeta is suggesting third, 27. Okay, so anyone else? Otherwise, anyway, I got the two answers, so I will discuss about that. Now see, in questions now, don't miss the crucial informations which is always been mentioned in the words. Like here, the important information is zero total spin. Now let us discuss about it and let us solve it. Since the electron excited state, it is D1 P1, right? So what way you can solve it? For D1, you need to calculate what will be the microstate? 10. For P1, if you will calculate, okay, for D1, what is the pigeonhole diagram? This one. Now let us discuss about P1. So in case of P1, 6 microstate are possible. So as per the formula, you can multiply up these two and you will get the information. But be careful. Here, the obligation is zero total. So what you need to do, you have to draw the pigeonhole diagram for P1. Now, in the right hand side, I have shown. Now see, the question is zero total spin, right? So suppose for this, you are going to take this as a complement. Whether it is having zero total spin? No, it is not. So with respect to this, the only possible configuration which is feasible is this one. This one, right? Overall spin will be 0. Similarly for this, again this one. For this, this one. So what I want to convey that basically the half of the possibilities has been removed. So in this case, the total feasibility, if you will see, suppose I'm taking here this lower, this 5 and this 3. So what you need to do, you have to make a multiplication of 5 multiplied by 3. So the overall answer will be 15. See, why don't we take this one? You are having a freedom. You can take this one, this red one and this red one. But in that case, you cannot take this pink one because you have already taken one set. No, you are going to get the same information. So either you exclude this and take the remaining 5 from D1 and remaining 3 from P1, or you can exclude these and take the remaining 2. So the answer will be 15 like this. Okay. Okay, let us discuss about the LS coupling. Now see, a single electron which is rotating, there are the two vectors are going to be implemented. One is because of orbital motion and second because of its own spin. And if you remember in physics, it has been discussed that if the two forces are the vector quantities are going to be implemented, then you are then the object is going to face the resultant of that, and that is called LS coupling for low atomic number. Otherwise, for higher atomic number, this is called JJ coupling. Okay, since we are talking about the transition metal till 30, so we will only confine ourselves for LS coupling. So for LS coupling, what will be the possible J? It can be higher to lower. So it will be L plus S and minimum will be L minus S, right? So for D3, if I will ask, what will be the S? It will be 3 by 2. Right now we are talking about ground state. So what we will do, we will fill up 1 electron in each orbital. So overall spin will be 3 by 2. And if you will calculate the L, what it will come? 2 multiplied by 1 plus 1 multiplied by 1 plus 1 multiplied by 0. So the value will become 3, right? Now, just now we told that J possible can be calculated with the help of L plus S to L minus S. So 3 by 2 plus 3. Solve it. It will be 9 by 2. And what will be the minimum? Again, you have to subtract it. Then it is 3 by 2. So the J possible can be ranged from 9 by 2 to 3 by 2. Okay? Up for F3, you do it. Right? I'm skipping now. Now, see, now even for D3, if you will see how many possible values you have got it, 4, 9 by 2, 7 by 2, 5 by 2, 3 by 2. Now the question is which is going to be implemented. So that can be calculated by the identification of J valued values. So what is the approach? So now you have to see whether L is greater than S or S is greater than L. So in case of L, which is greater than S, the total valid value will be 2S plus 1. Okay. So, and suppose S is greater than, then in that case, the J valid will be 2L plus 1. Okay. Actually, for D3, you have already calculated this. You see this on the left hand side. J possible. Now J valid. Since here, if you will see, L is greater than S, right? L ki value kya hai? 3. For S, it is 3 by 2. So which formula you are going to implement? The second one, that is 2L plus 1. Sorry, L is greater than S, right? So what formula you are going to apply? Lower one. So it is 2S plus 1. So 2 multiplied by 3 by 2 plus 1. So 4 values are possible. So basically these all 4 possible J values are valid values. Clear hai? Even for P3, if you will see, in that case, the only possible J valid is 1. So if you will calculate J possible, 4 possibilities are there: 3 by 2, 1 by 2, minus 3 by 2, and minus 1 by 2. But how many are valid? Only 1, and that is 3 by 2. Okay. So the ground state term will be 4S 3 by 2. Okay. Again, there is a question, the configurations, I guess you will solve it now. Now among the J valid, which one will be the correct? That is another thing. So remember, if the configuration is less than half filled, then lowest J value will be used. And suppose the electronic configuration is more than half filled, then highest value will be used for the ground state term. Okay. Still I'm having a time or not? Okay, I will take 5 more minutes. One question I want to solve. For Fe plus 2, find out the correct J valued value. So Fe plus 2, what is the configuration? It is D6. So for D6, it is S value will be 2. For L, it is again 2. Now what will be the J possible? L plus S to L minus S. So 4 to 0, all the values are J possible. Now how do you calculate J valid? See, in this case, since L and S both are the same, so any of the formula is going to be work out. So all 5 are basically J valid. Now you have to find out correct J valid. So ground state, then in that case, it will be 4. Why? Because I just now told you, if the electronic configuration is more than half filled, then highest J value will be used for the ground state term. So you got it, J valid is 4, 3, 2, 1, 0. So basically highest value is 4. So J valid for the ground state will be D4, 5D4. Right? Now see, the same question has been asked in GATE 2010. The term symbol of iron in given complex FeCN6 4- is. That's my last question for today's lecture. I'm sorry, I cannot cover. I have so many things to discuss, but I do have a time limitations. So anyway, let us solve these questions first. I would be happy if I will get a good response from the student for this particular questions. The term symbol for Fe in complex FeCN6 4- is. You just see in the left hand side, I have already solved Fe plus 2, but still some tricky thing is involved. Tell me. I'm waiting. Do it quick. No response. Okay, I will solve it for you. Actually, for any given complex, first you have to find out the electronic configurations. Since cyanide is a strong field ligand, so in this case, inner pairing will be there. and low spin complex like this. Then you calculate it. So here the value of L is 6. So with respect to 6, what symbol is going to be used? It is I. And if you calculate the value of S, it will become 0. S is equal to 0. So what will be J? L plus S, that is 6 plus 0. So it's a very straightforward question. So the answer will be 1I6. Another question is again from the gate. The ground state term symbol for rhodium is 4F. So the electronic configuration will be. It's a homework from my end. And I think that's all from my end, actually. Still so many things are there. But anyway, we will cover it whenever I will get more chance for this. Okay, so students, now the forum is open. If you have any sort of doubt, you can ask to me.
If anyone have doubt, then please unmute and ask.
Anyone?
So it was indeed a great presentation, sir. Thank you very much, sir, for giving your valuable insights on electronic spectra in transition elements. So, sir explained very nicely and easily DD transition, electronic distribution in various orbitals, calculation of microstate, term symbol, LS coupling. So thank you so much, sir, for sharing giving this valuable information to us. Thank you.
Thank you, ma'am.
Thank you, Rohit sir.
Thank you, sir. Thank you so much. It's indeed pleasure to be with you all. And thank you, Professor Hemant, for giving me opportunity to share my own understanding about the subject. Hope I have solved the purpose. And
Yes,
that's all. Thank you. Thank you so much.
thank you, sir.
Now we are moving to our third session, which is on problems on stereochemistry. So it's my privilege to introduce our resource person for this session. He is none other than very dynamic and energetic personality, Dr. H.N. Akolkar sir, Head Department of Chemistry, Abasaheb Marathe Arts New Commerce Science College, Rajapur. So I request you, sir, to start your presentation.
Thank you, ma'am. As Kulkarni sir already taken the basics of stereochemistry, so I will directly start the problem solving session. Problems based on stereochemistry. All these problems, whichever I am going to discuss, all these problems are asked in various competitive examination like NET, SET, JAM, GATE. So I have collected these problems from the previous question papers. So I am going to discuss one by one. Okay. So this is first problem. The least stable conformation. Sorry. So here 4 options are given, which is the least stable conformation. Least stable. Yes. Which is the least stable conformation of 2-methyl butane. So for this, we should know the Newman projection formulas. Okay. So here 4 options are given. So here generally 2 types. मी तुम्हाला 2 सांगतो. त्यातून तुम्ही आयडेंटिफाय करा. दिस इज स्टॅगर्ड कन्फर्मेशन. Staggered confirmation, and this one is eclipsed confirmation. This is eclipsed one. This is just a backbone. Okay, so generally staggered confirmations are stable than eclipsed confirmation. So ही एक hint है. This is the hint. So here you can find out the out of these four which is stable and which is least stable. Okay, so these C and D, these two are staggered confirmations, right? So all atoms are away from 60 degree each other. Okay, and these two confirmations are eclipsed confirmations. So our answer is in between these two, A and B. So if the similar groups, suppose CH3, they are eclipsed to each other, that means 0 degree angle is present in between these two CH3, then this is least stable confirmation. This is least stable. Okay, if they are apart from each other by 60 degree like this, CH3, the angle between two CH3 is 60 degree, this is gauge confirmation. This confirmation is called gauge. So this is in between these two, gauge confirmation. So stability order is staggered is more stable, then gauge confirmation, and then least stable is eclipsed. So in between A and B, which is correct answer? Can anyone? Chat box मध्ये लिहिलं तरी चालेल. So answer B is right. So here answer B is correct, because if you see here CH3 and CH3, these are eclipsed to each other. Okay, here all are 120 degree apart from each other. So therefore the least stable confirmation is B. So this is correct answer. If similar question is asked for most stable confirmation, most stable साठी विचारला असता तर कोणता आला असता? Which is most stable confirmation of these two methyl butane? Yes, right. Chaitanya, Pooja, all of you are giving the right answer. So D is the most stable. This is most stable confirmation. Okay. So remember this staggered Newman, all these are given in Newman projection formulae. Okay. So staggered, eclipsed, and gauge confirmation. So if you see here, all CH3 are close to each other in C confirmation. So therefore, the most stable and least stable is B. Okay. Okay, next question is this. The most stable confirmation of 2-fluoroethanol is. The most stable confirmation of 2-fluoroethanol is. Yes, most stable. So again, if you see here, this is eclipsed one. First one is eclipsed. This is also eclipsed. Right? If you see the backbone or the confirmation, staggered and eclipsed. So A and C are eclipsed confirmations. So these are least stable confirmation. So these answers are ruled out, right? आता राहिला प्रश्न B आणि D मध्ये. तर B आणि D मध्ये जास्त स्टेबल कोण आहे? Which is more stable in between B and D? Most of you are saying D. Okay, Chaitanya is saying B. Okay, Chaitanya B म्हणतोय, बाकी D म्हणतायत. Okay, हा एक थोडासा फसवा प्रश्न आहे. In such question, जर तुम्हाला असे काही सबस्टिट्युएंट्स आले, सपोज CHO अँड OH, जसं याच्यामध्ये फ्लोरीन आणि OH आलाय बघा, फ्लोरीन अँड OH इज देअर. So like this COOH, OH, then NO2OH, OH and OH. Okay, if such type of substituents are present on carbon number 1 and 2, suppose, okay, then this conformation is more stable, B. Instead of D, B is more stable, because in such problem, what happens here, this OH and fluorine, it forms hydrogen bonding. So hydrogen bonding, intramolecular hydrogen bonding is present. Okay, intramolecular hydrogen bonding is present. So because of this intramolecular hydrogen bonding, it makes this conformation more stable. This is the most stable conformation. Okay, आणि जर अशी हायड्रोजन बॉन्डिंग नसेल प्रेझेंट, इफ सच टाइप ऑफ हायड्रोजन बॉन्डिंग इज ऍबसेंट, then conformation D is more stable, because all bulkier group are 180 degree apart from each other. So therefore conformation D is more stable if hydrogen bonding is absent. But if hydrogen bonding is present, for this hydrogen bonding, for example, these type of groups should be present, fluorine, OH, then this combination, if these combinations are present, most of the time this question is also asked. Okay, OH, OH, then in that case also this type of conformation is more stable when they are 60 degree apart from each other. The angle between these two is 60 degree. Okay, त्याला आपण गॉच म्हणतो. So such type of problems were asked in the previous question papers. So remember these combinations, so you can easily solve these problems. Okay, समझ लगा है? Yes or no? Okay, yes, thank you. The next problem, the gauge interaction values for MEME, MEBR and BRBR are 3.3, 0.8 and 3 kilojoule per mole respectively. Among the following, the most stable conformation of 2,3-dibromobutane is. So here most stable conformation is asked, most stable, and here the values of butane gauge interactions are given. MEME it is 3.3, for MEBR when they are present at 60 degree, then its energy is 0.8, and for BRBR it is 3 kilojoule per mole. So which is most stable? Yes, most stable. So similar groups should be away from each other, they are apart from each other, asa conformation शोधायचा. So here BRBR come closer to each other, here also BRBR come close to each other, here also BRBR come close. So that means only one conformation is there where BR at BR, bromine and bromine are 180 degree apart, methyl and methyl also 180 degree apart from each other. So therefore most stable conformation is B. Okay, B is most stable. Right, and which is the least stable? This is most stable, and which is least stable? Yeah, A. A is least stable. Very good. This is least stable conformation because BRBR gauge interaction is 3 kilojoule, MEME it is 3.3, so it becomes 6.3, and 1 MEBR is there plus 0.8, 6.3 plus 0.8 it is 7.1. Okay, so the least stable conformation is A, most stable conformation is B. Very good. Okay. Next problem is on cyclohexane, 1,2-dimethyl cyclohexane. So energy difference between the two conformation of 1,2-dimethyl cyclohexane is. So for this, all of you should know the energies of this disubstituted cyclohexane. So 1,2-dimethyl cyclohexane. So three type of conformations are possible: axial equatorial, equatorial equatorial, and axial axial. Okay. So energy of these energy of these conformations are: for axial equatorial, there are 3 butane-Gauge interactions are present. This is axial and this is equatorial. Okay. So there are total 3 butane-Gauge are present for this conformation. Okay. So when one methyl group is present at axial, there are 2 butane-Gauge interactions are possible for this axial group. Okay. And plus one more butane-Gauge is present in between this axial and equatorial. So this angle is also 60 degree. Those one more butane-Gauge interaction is there. So therefore, total 3 butane-Gauge interactions are present. So therefore, energy of axial equatorial is 2.7 kilocalorie per mole. Okay. Equatorial equatorial. For equatorial equatorial, इथे दिलेलं नाहीये. This is equatorial equatorial. So for equatorial equatorial, this is 1,2-dimethyl cyclohexane, and in between equatorial equatorial, there is also one butane-Gauge is present between these 2 equatorial methyl groups, because the angle of these 2 methyl group is 60 degree. So therefore, one butane-Gauge is there. Hence, energy is 0.9 kilocalorie. And for axial axial, here this is axial axial. So one axial gives 2 butane-Gauge interactions. So 2 axial will give 4 butane-Gauge interactions. So therefore, total energy of this axial axial, it is 3.6 kilocalorie per mole. Now, the energy difference between the two conformations of 1,2-dimethyl cyclohexane is, yes. Now the energy difference 3.6 minus, yes, 3.6 minus 2.7, it is 0.9. So correct answer is this, A, 0.9 kilocalorie per mole. This is the energy difference between these two conformations. Okay. Next, give the energy of each Gauge butane interaction. Given the energy of each Gauge butane interaction is 0.9 kilocalorie per mole. So delta G value of the following reaction is. What is the delta G value of this reaction? Yes. So this is again 1,2-di substituted cyclohexane, right? So this is trans and this is cis. Because as both methyl groups are on same side, this is cis, and here in first case this is trans. So trans 1,2-dimethyl cyclohexane. So here for trans, suppose if we take axial methyl, then at carbon number 2 it is trans, right? This is CH3 CH3. This is trans 1,2-dimethyl cyclohexane, because both methyl groups are on opposite side. Also, we can show this trans like this. Both can be present at equatorial equatorial. This is axial axial, this is equatorial equatorial. These are the two representation of trans 1,2-dimethyl cyclohexane. Okay, and this cis मध्ये आपल्याकडे एकच ऑप्शन असतो, एक ऍक्सियल आणि एक इक्वेटोरियल. बोथ आर ऑन सेम साइड. दिस इज cis, axial, equatorial. Now The energy of AA, it is 3.6. As we know that equatorial, it is 0.9. And for cis, it is 2.7. Yes. It is 2.7. Now, if you see the reaction carefully, backward and forward reaction. So here, this backward reaction, this reaction is more favorable, right? If you see the arrows, which is more favorable, cis to trans is more favorable. This means trans is more stable. And here, equatorial is written at the bottom, right? So this is EE conformation because this trans is more stable. And axial equatorial cis, there is only one option. You have energy is 2.7. Then what is the delta G? Delta G means the difference between the energies. दोन्ही मधल्या एनर्जीचा डिफरन्स. आता cis तर माहिती आहे 2.7 आहे आणि ट्रान्स ई कळालाय इट इज 0.9. So hence the energy difference between these two conformation is, so delta G of the following reaction is 1.8 kilocalorie per mole. So correct answer is this B, 1.8. 2.7 minus 0.9. It is 1.8. Okay. Yes, 1.8. Saurabh, Shushali, very good. Okay, next is this. Among the structures given below, the most stable conformation for the following compound is, which is most stable conformation. So all these are cis, all methyl groups are cis, they are on same side, right? Suppose 1, 2, 3, 4. Relation between 1, 4 is cis, between 1, 3, 1, 2 is cis, and in between 2 and 4 is also cis. All are on same side. Okay. Now let's check the stereochemistry. If you see the first structure, this methyl group is on above side, right? It is on top side. Here, this also goes above, this also goes above. So this is cis. Okay. So relation between all CH3 is cis. If you see here, one goes upward, one goes downward. For B, if you see here, this goes upward and this goes downward. That means this is trans. Relation is trans. Okay. If you see here, this is upward, this is upward, this is upward. Again, cis. Here, this is downward, this is upward. Okay. So this is trans conformation. That means two conformations are ruled out, D and B. So these are incorrect one. आता या दोघांपैकी सांगायचं which is most stable, which is most stable conformation. Most stable conformation साठी जितके जास्त ग्रुप तुमच्या ऍक्सियल ला असतील तितका तो जास्त स्टेबल. The more number of groups are present on equatorial, that conformation is more stable. Okay. So in case of A, there are two methyl groups are on axial. Here two methyl groups are on axial, and here two methyl groups are on equatorial position. So more the number of methyl groups or any bulkier group is present on equatorial, that conformation is more stable. So hence conformation C is most stable conformation. So correct answer is this C, because two methyl groups are present on equatorial position. Therefore conformation C is more stable. Okay. कोणी दिलं होतं का उत्तर? नाही. I think A answer दिलं होतं, which is incorrect. Okay. So most stable is C. कळालं का आता हे? Yeah. Okay. Thank you. Next problem is this. In the most stable conformation of trans 1 tertiary butyl 3-methyl cyclohexane, the substituents at C1 and C3 respectively are 1 tertiary butyl 3-methyl cyclohexane, The substituents at C1 and C3 respectively are. So for this, we have to write down the planar structure of tertiary butyl group. This is, suppose आपण wedge line ने जर draw केलं, suppose this is 1, 2, 3 and trans. So methyl group is at downward side. This is tertiary butyl group. Upward घेतलं तर हे downward होईल. Remember always, whenever you are going to draw the conformation for bulkier group, always remember bulkier group should be present on equatorial position. This is called locking of conformation. We have to lock the conformation by keeping the bulkier group at equatorial position. तर आपल्याला नेहमी लक्षात ठेवा की bulkier group जो आहे, it should be present at equatorial position. So tertiary butyl group आपण upward side equatorial ला ठेवलाय. Then 1, 2, 3. Then methyl group is present at downward side, right? So this is axial position. That means at carbon number 1, group is present at equatorial, and at carbon number 3, the group is present at axial. So correct answer is equatorial, axial. So answer C is correct. Equatorial, axial, because bulkier groups always keep at equatorial position. नेहमी लक्षात ठेवा की bulkier group जर असेल तर तो नेहमी equatorial ला ठेवायचा आहे. So the correct answer is C. Okay. Next. Consider the following statements about cis-trans decalene. This is decalene system. One more cyclohexane is added. Decalene मध्ये आणखी एक 2 cyclohexane. This is the structure for decalene. This. मग यामध्ये 2 conformation आहे. cis and trans conformation is there. So hydrogen, hydrogen, these are present on opposite side. It is upward, this is downward. This is trans decalene, and this hydrogen is upward and this hydrogen is also upward. This is cis decalene. Energy of trans decalene is 0. And energy of cis decalene, as it has this axial bond, it creates 2 butane gauge interaction. And for a ring, this is axial. This bond is axial. So therefore, there are total 3 butane gauge interactions are present in cis decalene. So energy is 2.7. Energy of the conformation is 2.7 kilocalorie per mole. And for trans decalene, there is no axial bond, hence energy is 0. Now let's see the statements. Okay, cis isomer is more stable than trans isomer. It is not correct, right? Trans isomer energy is 0, it is more stable. So this is not correct. Trans isomer is more stable than cis isomer. Yes, as it has 0 energy, trans is more stable. Trans isomer undergoes ring flip and cis isomer undergoes ring flip. Which is correct, C or D? Which will undergo ring flip? दोघांपैकी ring flip कोण करेल, cis की trans? Always it goes for from less stable to more stable. Ring flip कधी होते, less stable to more stable जायचं असेल तर. More stable to less stable होणार नाही. Okay. So cis isomer is less stable. It undergoes ring flip. Okay, so D is correct. Cis isomer is less stable, so it undergoes ring flip and then convert it into trans decalene. Okay, so B and D are the correct answers. So answer is A. Okay, समझते क्या है? Yes. Okay. Okay, next is this. The most stable conformation of the following compound is. Most stable conformation of the following compound is. Yes, which is most correct. Most stable. Yes. Yeah, A. Okay. Aisha Tamoli says A. Saurabh C. Sangeeta B. Chaitanya C. Yes. C. Okay. Sushali is also saying C. So correct answer is C. Very good. If you see a bulkier group here, bulkier group present at axial, it makes this conformation less stable. This is boat conformation. This is half chair, right? Yeah, already less stable as well. Okay, so therefore our choice is in between these two. Also, in space, these two are come closer to each other and make hydrogen bonding. So this intramolecular hydrogen bonding also stabilize this conformation, intramolecular hydrogen bonding. So most stable conformation is C. Very good. Next, the most stable conformation of 5-hydroxy 1,3-dioxane is, yes, which is more correct? A, B, C, D. Okay. This answer is very simple. Again, reason is hydrogen bonding. Reason is hydrogen bonding. Okay, Saurabh says yes, yes, A, okay. Yes, A is correct. A is correct one. Yes. So this hydroxy group form hydrogen bond with these oxygens because all are present on same side, top side. If you see between C and D, there is a boat conformation. So these are least stable, B and D. In case of B, this OH is present at equatorial, but even though this OH is present at axial, this will form intramolecular hydrogen bonding. Due to intramolecular hydrogen bonding, A conformation is most stable. Okay. Similar example again. Among the structures given below, the one that corresponds to the most stable conformation of compound A is, yes. Okay. Again A, very good. So conformation A is more stable again because this methyl group is present at equatorial position. आपल्याला ते पण पाहिजे. The methyl group is present at equatorial. If you see C and D, methyl group is present at axial. So therefore, these are a least stable conformation as methyl group are present at axial. So our choice is in between A and B. So here, due to intramolecular hydrogen bonding and methyl group is present at equatorial, this makes compound A more stable. Very good. Okay, what is the relationship between compound 1 and 2? What is the relationship between compound 1 and 2? Are they diastereomers, enantiomers, conformational isomers, or constitutional isomers? Yes. Yeah, very good. बरोबर आहेत तुमचे आन्सर्स. So compound A, sorry, option A is correct, diastereomers. Okay. If you see the directions of all groups, so all methyl groups are pointing upward, so all are cis. If you see here, two cis and one goes downward, so this is trans, it goes downward, so therefore there is only one carbon where configuration is changed. Suppose if you see here 1, 2, 3, 4, 1 is present at the top, 2 here and 4 here. And in case of second, this is first case. In case of second, sorry, okay, this is carbon number 1, 2, 3, 4. So there is change at this carbon, right? Here, carbon number 1. Carbon number 1. Here, stereochemistry change. So Kulkarni sir said that RRSS configurations. So from that we can easily find out whether the conformations are diastereomer, enantiomer or identical. So this is diastereomer. जर सगळे चेंज झाले असते, if all positions are changed, suppose downward, downward and downward, then all should have opposite configurations. So therefore the pair should be enantiomer. If such things are given, then जर असं झालं असतं की सगळेच डाऊनवर्ड आहेत आणि एका बाजूला सगळेच अपवर्ड आहेत, तर त्या केस मध्ये ते enantiomers झाले असते. ओके, then problem, only 2 problems are left, then we will stop. These problems already taken by Kulkarni sir. The specific rotation for S+2 butanol is 10 degree ml per GDM. The observed optical rotation of a sample composed of mixture of R and S2 butanol is -45 degree. If the path length is, cell path length is 0.6 dm and the concentration of 2-butanol in the sample is 0.15 gram per ml, the percentage of R and S enantiomer in the sample are. What is the percentage of R and S? Can anyone guess? Yes. So for this alpha, for what is given, that we will see given things. Alpha for specific rotation is given. Specific rotation is 10 degree, right? Then what is given? This is pure. This is for pure, as use plus sign, 2 butanol. This is specific for S plus 2 butanol. Okay, specific rotation. This is for pure compound. Then next thing is alpha observed. Observed optical rotation. It is for the mixture. It is given -0.45 degree. Again, symbol minus is there. Okay. Then path length, cell path length is given. It is 0.6 dm and concentration is given. C is also given 0.15 gram per ml. So for this specific rotation of a mixture, that we have to calculate first. This is for pure compound. specific rotation of pure compound is given. Now we have to find out specific rotation for mixture. Okay, so this is for mixture. This is equal to observed rotation divided by path length and concentration. Observed rotation is 0.45 degree. Length is given 0.6. Concentration is given 0.15. So the answer is, it is, yes, it is 1/2, right? So 0.5. Sorry. एक minute. Okay. So here the answer is 5 degree. Okay, minus 5 degree. This is specific rotation for the mixture. And then we have to find out the enantiomeric excess. Enantiomeric excess, the formula for enantiomeric excess is alpha for the mixture and alpha for the pure. Okay, alpha for mixture, it is that we have calculated, it is 0.5, and for pure it is 10, right? They were 10, so multiplied by 100, so this is equal to 50% enantiomeric excess, and this is for R conformation, clockwise, plus here plus sign is given, so therefore this enantiomeric excess is for R conformation. Okay, 50% enantiomeric excess R च जर आला असेल तर S किती असेल, which cancels the remaining R. So remaining is 50%. So 50 च्या निम्म करा, 25, right? So total 100 असेल, 100 पैकी 50 enantiomeric excess आहे आणि 50 उरलेले आहेत. तर ह्या 50 चं काय करायचं, हाफ करायचं, 25 plus 25, because 25S cancels 25R. Okay, so therefore the total R, percentage of R is 50 plus 25, it is 75, and for yes it is 25. So correct answer is D. Okay, so correct answer is D. R 75% and yes 25%. So this is how we have to we can calculate the observed rotation, enantiomeric excess, specific rotation, and the percentage of R and S in the sample. Okay. The next question, similar as an optically pure organic compound has specific rotation of plus 40 degree. The optical purity of the sample that exhibits specific rotation of plus 32 degree is, yes. Sorry. So here optical purity, this problem was taken by Kulkarni sir. This type of problem, not this type of problem. So optical purity is calculated by optical purity is equal to alpha of sample divided by alpha specific rotation of pure enantiomer multiplied by 100. So alpha of sample is given, the optical purity of sample is given plus 32, and pure enantiomer it is 40 multiplied by 100. So the answer is, it is 80%. Okay, so correct answer is 80%. Yes. Correct answer is 80%. Okay. So these are the few more problems. Identify two enantiomers among the following compounds. So for this, you have to draw the Fisher projection formulas, and then you can easily find out the which two are enantiomers. Okay. So in between, in this problem, the C and D are enantiomers. C and D. मी एक तुम्हाला करून दाखवतो. So I will explain only one. You can draw other three and then identify really C and D are enantiomers or not. Okay. So I will take first compound. So this CH3, Br, hydrogen, Br, and hydrogen. So generally, for Fisher, we need to draw this molecule like this. Okay. So this rear carbon is as it is, Br and hydrogen. We have to rotate this front carbon by 180 degree. So CH3 will come here, and hydrogen, yes, where it goes? Here in 180 degree, and bromine will come here. Okay. Now, if you go for the Fisher, this CH3 are like this. For suppose this is front carbon, here this is suppose front, this is rear. Just write down the groups. To our left hand side, bromine are there for both carbons, and hydrogens are on our right hand side. So like this, you can draw the Fisher projection. Longest carbon chain select kara, दोन्ही CH3 bottom ला घ्या, so that you can easily write down the Fisher projection. Okay, Fisher projection लिहा, and then check the mirror image, because we have to find out enantiomers. So these two should be mirror images of each other. Okay. Okay. Next is this. The two compounds given below are enantiomer, identical, diastereomer, or regioisomers. Yes. Okay, someone says it is diastereomers. मी तरी diastereomer लिहिलंय. अजून yes, C. Okay. C. आता हे कसं आयडेंटिफाय करायचं? हाऊ टू आयडेंटिफाय वेदर द पेअर इज enantiomer, identical or diastereomer? सगळ्यात अगोदर जे कायरल सेंटर्स ते शोधा. Identify the chiral centers and assign R and S configuration. R-S configuration assign kar. Okay. Now in this case, there are two chiral centers. This one is and this one. So find out the R-S configuration of these two. If one isomer is having suppose R-R configuration and second one is having S-S configuration. Remember, suppose first compound is having RR, second compound is having SS, then both configurations are opposite. That means these are mirror images of each other. So then we can easily say that these are enantiomers. Okay. If first is RES, second is ESR, again opposite configurations, enantiomers. Suppose RR and RES change at only one chiral center, then these are diastereomers. दोन पैकी कुठल्याही एकावर चेंज झाला तर समजायचं हे डायस्टेरिओमर आहेत. दोन्हींचे अपोजिट झाले तर इनॅन्शिओमर आहेत. आणि दोन्ही सारखे असले देन हा पण RR आहे आणि हा पण RR आहे, फर्स्ट अँड सेकंड, देन these are identical. SS, SS again identical, SR, SR identical. So this is how you can identify the pair, whether these are enantiomer or regioisomers. Now tell me which is correct answer. Now find out RES. Sorry. Yes. C is not correct. Some people says that C is the option, but C is not correct. The correct answer is this, identical. This is identical. How? See here, priority for this, it is 1, this is 2, this is 3, this is clockwise, sorry, 1, 2, 3, and methyl group is fourth. Fourth priority group is at top side, right? So the confirmation is R. Even though it is anti-clockwise, the least priority group above side shown by a wedge line, then we have to change the configuration. Okay, so this is R, and for the second one it is 1, 2, and 3. This is anti-clockwise, this is yes, least priority group is at below or away from the observer. Similarly, if you find out the RS configuration for this one, again 1, 2, 3, this is clockwise R, methyl group least priority A, bottom side lag, so there is no change in configuration. And here this is 1, 2, and 3, R changes to yes. So RS and RS combination is, for first it is RS and for second it is again RS. So same configuration is there. So therefore both compounds are pair is identical. Okay. Thank you. Thank you for listening, patience, fully. Okay. Thank you.
If anyone have any doubts, then
कुणाला काही डाउट्स असतील तर विचारा. Yes.
Okay, thank you, sir. So in this session, we listen Dr. Akolkar sir, who has 11 years UG/PG experience. And his research interest is synthetic organic chemistry, heterocyclic chemistry, and DIN chemistry. So he has completed 2 research products granted by UGC of 1,60,000, and second one granted by BCUD, Savitribai Phule University, Pune, of 2,20,000. And about 48 papers are published by Akolkar sir, as well as he has got one Indian patent. And also he has present 13 papers in national and international conferences. He is a reviewer of a very reputed journal, that is Indian Journal of Chemistry, Section B. And he also delivers lectures on stereochemistry and spectroscopy as a resource person in various institutes. So, sir, we are so pleasure to listen you in this session. Thank you so much, sir, for discussing problems on stereochemistry. Thank you once again.
Thank you. Tomorrow we will join sharp at 9:50 AM. उद्या सकाळी आपण बरोबर 9:50 ला भेटूयात. उद्या पण खूप चांगले लेक्चर्स आहेत. तर बरोबर मी तुम्हाला पुन्हा एकदा लिंक शेअर करेल. उद्या आपण बरोबर 9:50 ला भेटूयात. ओके, थँक्यू.